Okay, now you are online. So today it's going to be a talk from Wolfgang Maier, who is a specialist of Bushveld and layering intrusion. So he comes from Cardiff and he got his PhD in Rhodes University in South Africa. After that, he stayed in South Africa for a while as a lecturer and go for some position in Chicoutimi for a few years, 4 years, I think, and go in Australia to work with Stefan Barnes, I think.
No, but in the same city.
Okay, the same city. Okay. And now, after that, he has been in Ulu, and now he's in Cardiff. So, yeah, here your favorite talk, Bushveld Petrogenesis.
Can we switch, turn the lights down a little bit?
Yeah.
Yeah, so welcome everybody. Also to the people on online, if there are any. From Oulu, I think, and Luleå and Reykjavik, and perhaps even from Greenland, some. Right, so that's very nice. My old friends and colleagues from Oulu, maybe some of them watch this too. So welcome to everybody. And I have 3 hours, I think, altogether.
Yeah.
So with a break in between, 3 hours to talk about the Bushveld complex. I have 200 slides. Most of them are photographs of the field and or thin sections, mostly field photographs. There are just a few geochemical diagrams, not a hell of a lot, maybe 10 altogether, that's all, or 15. So it shouldn't be, it should be reasonably entertaining for most people, I hope. Now, this before I start here, before I go into the topic seriously here, this is a slide from overview of the Bushveld complex from Pretoria, about 50 kilometers to the west of Pretoria, at a place called Hartbeespoort Dam, which Hartbeespoort Dam you see here in the distance. This is a favorite, very sort of popular weekend destination for Pretoria people to come and go to the lake here, do water sports. There's also a big South African nuclear energy research facility just on the other side of the lake that is still used for some analytical purposes. They had their big nuclear energy program there until the end of apartheid, which then terminated. And the Bushveld complex, of course, is to our right here. This is this prominent ridge of rocks that you see here. That's called the Magaliesberg quartzite. It's a very extensive quartzite horizon in the Transvaal supergroup sedimentary sequence throughout northern South Africa, much of northern South Africa. It's a several tens to hundreds of meters thick quartzite that, as you can see here, dips gently about 20 degrees towards the and underneath the Bushveld complex. And we are here at the southern margin edge of the Bushveld complex. And wherever you go around the Bushveld complex, this gigantic 400 kilometer wide intrusion, you see in many places, in most places, the Magaliesberg quartzite being its floor rock and dipping towards the center of this giant lopolitic structure, like a soup dish-like structure. So Magaliesberg quartzite, and you can also see here that there is a major graben fault right ahead of us, and this is called the Britsgraben. And displacement is several hundred meters, 100 or 200 meters or so. And this is interesting for us because when we look at the Bushveld, the layered sequence of the Bushveld sequence here, it goes across the graben, but it thins somewhat in the graben. So that suggests that this graben was a thin Bushveld structure, and possibly related to the filling and emplacement of the Bushveld complex. And I suspect, or people suspect, that when the Bushveld complex was filled and emplaced, of course, there were a lot of tectonic activity, lots of earthquakes, seismic activity, and this graben here, this Britsgraben, would have been one of the expressions of this seismic activity. Good. We come back to this a little bit later. Okay, so why Bushveld? Bushveld, of course, is a very large igneous body. It's also the world's largest ore deposit. This is why people are interested in studying it. It's really the pillar of the South African, one of the main pillars of the South African industry. Total value of the deposit mined so far and still in the ground is on the order of 1.4 trillion US dollars, 2004 figures. This won't have changed a lot. So it's really a very important ore deposit, and you may feel the same as I do, but studying, important geological phenomena, big ore deposits or famous outcrops and intrusions, is particularly interesting to us because people are interested in this. So you get a lot of feedback and a lot of interest, and of course a lot of more funding also from funding agencies in industry. So that's why we study the Bushveld complex. Lots of people study the Bushveld complex. Here, it's also not only the largest ore deposit on Earth, it's also by far the largest layered intrusion on Earth. And in two scales here, absolute and log, as you can see, the intrusion is really an order of magnitude larger than any other mafic-ultramafic layered intrusion. And this is one of the enigmas that people working on the Bushveld really are still struggling with, that we find difficult to explain. Why is this intrusion so much bigger than anything else on Earth? And of course, one of the things that we are puzzled by and wondering and pondering is, do unusual geological phenomena really require unusual processes? Or is it just a coincidence, maybe a preservational freak? We're not sure. I will talk much more about this in a little while. Right. Layered intrusions, of course, are a very common phenomenon on Earth. We have so far identified about 400. This is a picture here from your area of the world, Finland, and particularly has a lot of layered intrusions in Norway. I did this diagram when I was in Oulu University, so it's a focus on Finland. I'm sure you have almost certainly more layered intrusions in Norway than are on this picture here at the moment. But it appears that Archean cratons are particularly prone or particularly prospective to host layered intrusions, mafic-ultramafic intrusions. Here in Finland, we have about probably at least 30 in Finland and neighboring Kola Peninsula, Russian portion of the Karelian craton and Kola cratons. There are some very strongly mineralized ones here, notably Kemi, at the close to the Swedish border, which hosts the world's largest chromite deposit in a layered intrusion. I think right at the end of my presentation, I'll show you a slide from Kemi to give you a brief overlook how this thing looks like. There are other very well-known ones. There's Pennicut, which hosts platinum group element mineralization, Portimo and Koilisma. There is in Russia here the Monchegorsk complex that was mined for nickel, copper and PG since before the Second World War. It was actually Russia's main source for these metals before Norilsk was discovered and before they acquired Pechenga here after the Second World War from Finland. Not acquired, took it over. And then there's Fedorovo-Pansky here and Tundra too. There are other large intrusions here. I think Europe's largest actually is Burakovsky, which is down here. I don't have my glasses on now, so I struggle to see my own slides. And then there are smaller layered intrusions here along the southern craton of the Karelian, along the southern margin of the Karelian craton here. They host nickel mineralization. We're not going to look at these in a lot. This sort of belt seems to continue into Sweden with a number of large intrusions, feeder converts and layered intrusions here too. But in Norway, you got, after all, I have to put in my glasses to see the names. You got a number of intrusions up here near the Finnish border that are entirely unpronounceable for me. I think these must be Sami names, and the age of these actually is not entirely clear yet, but their petrology seems to be so similar to that many of these Finnish 2.4, 2.5 billion year old intrusions that many people suspect they are probably the same age. Here, then you have Tjohko-Aivia, that's still in Finland, and you have of course Sealand, and the intrusions of the Sealand province up here. They are interesting enough. I have a slide a little bit later in the presentation. In many regards, structurally and texturally and lithologically, they're similar to the Finnish intrusions. The Archean Proterozoic ones, they have also platinum group mineralization, but it's much younger saline. It's about 500 million, I seem to remember, something like that. It's also got platinum group element mineralization, so this is quite interesting. And actually, I talked to Melanie about this yesterday. I'd be interested to have a look at this place at some stage in the future, if the opportunity arises. Good. I go through this very quickly. This is the different metals that are mined in these layered intrusions here, that make up the value of these bodies here. You see in the Bushveld, it's mainly the PGE, and then some copper and nickel here. In most of the others, these are magmatic ore deposits in total globally. Here, the other big ones, Norilsk, Great Dyke, and Sudbury. Those are actually the, and then Stillwater, those are the ones that are mined for PGE. You see, Norilsk predominantly is actually the value is in nickel and copper, and somewhat less so in PGE. But in the Bushveld, the bulk of the value comes from platinum, palladium, and rhodium, and much less so copper and nickel. And actually, this does not contain vanadium and chromium. But again, the Bushveld is by far, by an order of magnitude, the largest layered ore deposit and layered intrusion on Earth, and we really don't understand this. This is an interesting slide from 1986 by Cox and Singer, US Geological Survey, and they grouped ore deposits in sort of according to what they felt at that time is our level of understanding of their origin. And as you can see, magmatic sulfide deposits, to which layered intrusion and PGE reefs belong, are right at the top of their list. So they felt in 1980, in the 1980s that we understand these ore deposits very well. And of course, I beg to differ. I think there's a lot of debate about the origin of the Bushveld, probably more so than about nickel-copper deposits. We really, it appears, don't understand the origin of these deposits yet at all. And so there you go. This is how very prominent scientists can go wrong. Right, so there we are. It's the largest ore deposit on Earth, largest intrusion by an order of magnitude, one of the largest igneous events, actually. Why is this so? We don't really understand at all, and this is one of the main things I'm going to do today in this presentation, to look at a couple of models and possibilities with you. Other important questions, how did this very fine scale and actually very extensive layering form? You should realize that when it comes to layered intrusion research, there are really several communities that work on these bodies. There's the ore deposit community that look on the platinum and chromium and vanadium deposits. And then there's also, and of course these people are also interested in the petrology of these intrusions, because to understand the deposits, you need to understand the petrology too, and perhaps even the geophysics and so on. But there's also another community who are predominantly interested in the petrology and the origin of layering and the emplacement of these bodies. And there is not always a hell of a lot of overlap between these two groups. So, so yeah, there are petrologists who are predominantly really puzzled about this very fine scale and laterally extensive layering. And this type of layering that you see here in the Bushveld complex in the lower critical zone can be traced for many kilometers, tens of kilometers in fact. And as you can see, it's very fine scale on the order of centimeters to decimeters. So how can this be explained? It remains a mystery actually. And then the origin of the sulfide reefs, chromite reefs, and magnetite reefs, of course, that is of very great economic importance in exploration. The classical model, I guess, to explain these intrusions was that we had, and that goes back to the 1960s and 50s and 60s and 70s, that we had a rain of sulfide droplets, that the magma reaches sulfide saturation, a rain of sulfide droplets sort of goes down, sinks down through the magma and accumulates at the top of the cumulate pile, the crystal pile. Most people do not believe really that this is, the model is so simple, and there are now several others that I discuss with you in a little while. But this is the sort of the classical model. And, accepting, within this classical model, accepting that the magma chamber was replenished numerous times by new influxes, these are the blue arrows that you see here, So numerous magma influxes, but in general that the magma, once it reached sulfide liquid saturation, that these sulfide droplets precipitated, sank down through the magma and accumulated at the top of the crystal path. Okay, let's look at the geological setting, the age, and the geophysics first. So this is where this body sits here in the center of the of southern Africa. There are several cratonic blocks there. There is the Kapval craton, the Zimbabwe craton, and there's another cratonic block whose name I now forgot. This is the Rehoboth craton, and these blocks here, these cratonic blocks, they have been dated. Rocks there have been dated down back to about 3.7 billion years old. So these are amongst the oldest pieces of cratonic craton on Earth that we have. Up here in Northern Europe, you have also cratonic rocks in Finland and in Kola, and little bits of it, I think, windows sticking out here in northern Norway that also go back to, I think in Finland they dated them to about 3.5 billion years. That's so just tiny little bit younger than these Archean ones here in these early Archean ones in southern Africa. There are very important famous geological features here in this region. There's the Bushveld complex, of course, here, 400 kilometers across, east, west, south, north, and part of the Bushveld complex is this one here too in Botswana called the Molopo Farms complex. And in fact here, same age also, right on the eastern margin of the craton are alkaline intrusions to which belongs the Phalaborwa igneous complex. So Bushveld event really is gigantic in extent, probably close to 1,000 kilometers in east-west. There are Bushveld-aged intrusions that go right down here to the Fredefort impact structure. So it's really a gigantic igneous event. There's the Great Dyke of Zimbabwe. There is the Witwatersrand goldfields with the Fredefort impact structure in the center, the world's largest meteorite impact structure. Barberton Greenstone Belt, the classical greenstone belt on Earth, where komadiites, were discovered, the magnesian lavas in 1969. Numerous really world-class famous geological phenomena and exposures here in southern Africa. And particularly when you work in economic geology, it's almost a must for student groups, for student excursions to go to southern Africa at least once, to South Africa at least once. There's also, of course, near Johannesburg here, what the locals call the cradle of humankind, the site where many of the important hominids were discovered. Perhaps not quite the oldest anymore, but many of the earliest and most important hominid finds were near Johannesburg. So really, and then of course the kimberlites with their diamond deposits all across the craton. Very, very many important geological features. So that's what interests us today here, the Bushveld complex. And so there it is, at least the center, the main portion of the Bushveld complex here. In green are the mafic-ultramafic layered rocks, as I told you, that form sort of a soup dish-like lopolitic body, dipping towards the center in all directions. Here and here, and our first picture of the presentation that I showed you right at the beginning here was taken about here. There's the Bredsgraben, this major feature. So we looked at it into it here. So that's the mafic-ultramafic rocks in green. On top of and intruding the mafic-ultramafic rocks are granitic rocks and rhyolites, felsic volcanics here, that are shown in blue. That's the granites, and the felsic volcanics in orange. They belong to the Bushveld event, pretty much almost the same age, maybe just slightly younger in the case of the granites, overlapping essentially with the mafic-ultramafic rocks, the volcanic rocks, the rhyolites, the felsic volcanics. So, you got it, everything there, the intrusive mafic-ultramafic rocks, granites, rhyolites, and then there's also a granophyric phase present. We subdivide the intrusion into western, eastern, northern, and here a hidden Bethel limb. And that's not so important now. A little bit on geophysics. I'm not a geophysicist, I don't know too much about it, but these are some images here, mainly gravity. So the gravity image here across the Bushveld, you can see clearly the mafic-ultramafic rocks, the dense mafic-ultramafic rocks sticking out in the west, the east, and the north, and the hidden Bethel lobe here. The absence of mafic-ultramafic rocks in the center, and also the lack of a gravity signature that was already established and identified in the 1950s, led to people initially proposing that the intrusion forms two sort of dipping sheets that are not connected in the center. Recently, this has been modified, this model, and people now believe that probably, yes, the intrusion is connected in the center, partly because the stratigraphy is very similar in the east and the west, but that there was, because, and this goes into sort of at the boundaries of my understanding of the whole problem, but here on this diagram, you can see the crustal thickness is much greater underneath the Bushveld, the center of the Bushveld. So people now believe that due to the higher crustal thickness, the moho has been slightly depressed, and this sort of compensates for the absence of seemingly absence of dense rocks here in the gravity image. And so people now believe that yes, the intrusion is connected at depth, but because in the center of the intrusion, the mafic-ultramafic rocks are at such great depth, we don't really see them in the gravity. So this is where we stand at the moment. It's probably connected at depth. I mean, the field geologists and petrologists suspected that for a long time, and in fact, in the 50s, when this sort of model came out that we have two dipping sheets here, there was a lot of skepticism amongst the field geologists. They just couldn't understand how can you form two intrusions whose stratigraphy really is quite similar, that are not connected. This is a little bit on age dating now. So the body is essentially 2055 roundabout. It's been known to be that roundabout that age for 30 years or so, 30, 40 years. Now in the last 5 years maybe, or 3 years, there is now new developments, lots of much more precise dating is happening. That's by several groups all across the world. Here, this is a recent PhD thesis by Corey Wall in Vancouver at UBC. His data is very, surprising or controversial if you want, certainly extremely surprising to me. Showing here that, the body mostly it's sort of between 2056 to 2060. But very importantly, when you look actually at the details here of the lower portions of that intrusion, you can see here that this horizon is at about 2060. We call that the bastard reef. I come to you to the stratigraphy in a moment. This one is at 2060. And below that, we have portions of the intrusion that appear to be younger by 2-3 million years. Here, the Mariansky Reef is about 2057. And in fact, the lower zone also appears to be younger. So if that is correct, this dating, then this suggests that the intrusion, that this big layered intrusion was emplaced as numerous sort of sill-like phases that perhaps were emplaced in a non-sequential manner. So some sills, later sills coming in above and below earlier sills. So that would be a kind of a revolution of our understanding of how layered intrusions form. The classical idea, of course, was that the ultramafic rocks at the bottom, they are sort of the early precipitates, perhaps of a large magma body. And then the more and more differentiated rocks represent later lower temperature cumulates derived from the same magma body. So what these sort of data possibly suggest now is that these big layered mafic-ultramafic intrusions are composite sills that were emplaced non-sequentially. And there's another paper just from last year by Mangel, who proposed something similar, but his ages were much closer together, and you see they're almost overlapping. So it's perhaps a little bit more contentious than the wall data, which clearly shows quite significant age differences, 1, 2, 3 million years. So that's where we are at the moment, and really what needs to be done now is, these results need to be duplicated to see whether that stands up, particularly here, these sort of very, very narrow age ranges and overlaps in the Mangel study. Somebody needs to go somewhere else in the Bushveld and sees whether he can find exactly the same things. I'm sure people are busy with doing that right now. Emplacement-wise, so schematically, this is how the intrusion looks like, actually, and this is not, I must change this. Here, this doesn't look like a lopolith, actually. This is, it should be exactly the other way around, but just schematically, it's sitting here on this Michalisberg quartzite in most of the Bushveld complex, which is a layer within a Transvaal supergroup. There is the basement granites. The intrusion locally cuts down through the quartzite, reaches the basement granite. In reality, of course, the intrusion is like a pancake, 400 kilometers wide, 8 kilometers thick. Now, what a really important thing is that the intrusion is underlain in most of its parts by a suite of sills, fine-grained sills here, that are schematically shown here. And these sills are important for petrologists because people have interpreted them to represent the parent magmas to these cumulates. One of the problems for petrologists in studying cumulate rocks is that, to figure out what was the parent magma to these cumulates. That's very difficult. A number of different approaches have been tried to do that. But one of the things that we quite like to see is, of course, chilled margins or fine-grained sills in the floor of the intrusions. These methods are not unambiguous. Of course, chilled margins and sills in the floor of the intrusion may be contaminated. They often are, and then it becomes quite difficult to make inferences on the parent magmas. But in the Bushveld complex, this suite of fine-grained sills here in the floor is considered to be relatively quite representative of the parent magmas to the intrusion. And so they have to be studied in a lot of detail. And we have actually, in the Bushveld, compared to many other layered intrusions, quite a good understanding of what the parent magmas look like. And I come back to that in a moment. Here is just a map from Ivanhoe's, one of Ivanhoe's operations in the northern lobe, showing you how complex the contacts to the floor rocks actually are. And the intrusion here, the base of the intrusion is shown here. That light green material here is critical zone. And then these blue rocks here, these are dolomitic and quartzitic and pilitic floor rocks of the intrusion. And you can see the brown stuff. These are lower zone sills. So these are cumulate rocks, ultramafic, mostly ultramafic cumulate rocks in the floor rocks. And you can see there is a large suite of sills actually in the floor rocks. The entire floor rock package has been very pervasively injected by these sills. That's important because these floor rocks, many of these floor rocks are dolomites. And of course, when you inject these high temperature, be that liquids or cumulate slurries into these dolomites, they will undergo very significant devolatilization. And this may have very significant implications for the Proterozoic atmosphere. So it's a very sort of, the contact between the intrusion and the sediments in many places is a bit diffuse. There are lots of sills injecting into the sediments, and this has consequences. What was the magma source to these to the Bushveld complex? This gigantic intrusion. Again, there's a lot of debate. We're not entirely sure. Two candidates are possible: the astenosphere and the lithosphere. Astenospheric mantle, lithospheric mantle, perhaps both. So the problem really we're facing is if the Bushveld complex sits here at the top of the Karpal crater, and there's more than 200 kilometers of lithosphere below it. If the complex is related to a mantle plume, then how did this magma manage to get through the 200 kilometers thick lithosphere? This is really the problem that people are trying to figure out. And one possibility, of course, is the Karpal, like many other cratons, is really a sort of an amalgamation of smaller protocratonic fragments or nuclei. And the diamond people, De Beers, and so they did a lot of work on the Karpal craton during the exploration activities and realized that there are at least 4 or 5 smaller fragments that make up the craton. So in rough sketch here in cross-section may look something like this. You have these suture zones between different cratonic fragments that may be used by Bushveld magma by a plume and then the resulting magmas to ascend through the craton. And it's possible that the Bushveld complex used one of these and interacted actually with crustal material in these suture zones. There's the seismic data here from the Karpal craton, and you can see this is generated by, there was a big American, United States, South African experiment, seismic experiment here in the early 2000s in Southern Africa. They produced these kind of maps. And this is the gravity map here, and you can see the boundaries of these cratonic fragments of the Karpal craton that were first identified by De Beers. Here there's one big lineament going up here, there's another lineament going through here. So there are at least 4 or 5 of these protocratonic fragments that make up the craton. And so the seismic tomography here of that the American South African program established, they came up with this sort of picture, and the colors here in this diagram indicate in blue the areas where seismic waves travel relatively fast. Okay, so these are maybe the relatively cold portions of the craton or relatively iron depleted portions of the craton. And then here in red and yellow are the areas where the seismic waves travel relatively slowly. So these are this, the slightly hotter perhaps or more iron-rich portions of the craton. And as you can see here, the craton boundary is defined here by this change here. And then in the middle of the craton, here, exactly where the Bushveld sits, we have an area here where the seismic tomography indicates the asthenospheric mantle either being closer or perhaps some major modification of the lithospheric mantle. And in cross-section, this is how it looks like. So from the south near Cape Town up into Zimbabwe. So this is a profile that goes from here up into Zimbabwe. So A to B. I'm sorry, this is BB plus. So B to B, can't remember. B little thing on top here. B prime, that's it. So from B to B prime here, Cape Town to Zimbabwe, there is the craton, and there is this area overlying the Bushveld complex here, where the asthenosphere has come closer to surface, or perhaps the entire lithosphere has been modified, refertilized by the by Bushveld magmas. So this, the geophysicists still work on this problem. People like Sue Webb and Witwatersrand University, very intriguing. Another possibility is that when we look again at this Karpal craton and this different lineaments, there's a major lineament that goes across here that essentially defines the Limpopo orogenic belt, and another one that goes through here, the so-called Tabazimbi merchant lineament. And people speculate whether around about 2 billion year old around about 2 billion year old subduction zone here generated some back arc spreading that allowed magma to ascend to the surface. So it's a possibility, but there's very little outcrop here in this area, in the Kalahari. And so this is difficult to really test and constrain this model. There are some volcanic rocks around about that age occurring across here, but very, very little outcrop. So this is related. This is a paper by Silver, geophysicist from the US, who worked on this in 2000s, in the early 2000s, and essentially also proposing a model whereby here compressional forces acting on the Karpal craton due to collision of the craton with the Zimbabwe craton here remobilized and opened structures along the Tabazimbi merchant lineament here in this area that allowed the Bushveld magma to intrude. So this would be some kind of a transpressional rift model. And then we also had more recently, a paper by a Swedish group that it's quite an interesting model. They had a model essentially of delamination resulting in Bushveld magmatism. So the story goes like this: around about 2.7 billion years, so 700 million years before Bushveld emplacement, we had the large Ventersdorp continental flood basalts in southern Africa that, by the way, are a similar event at exactly the same time happening in the Pilbara craton over in Australia, which led to people to suggest that the Pilbara and Karpal were linked at that time. So the big Ventersdorp flood basalts, 2.7 here, generating here all these dikes and flood basalts and some thickening of the lithospheric mantle. This led then ultimately here to some the formation of the Transvaal sedimentary basin subsidence, and then a delamination of the plume residue, allowing suddenly a stenospheric magma to move into the thin lithospheric mantle and melting and producing Bushveld event. So this sort of model is based on the dating of a sill suite, sill and dike suite all around the Bushveld event, that they argue these dikes that they dated at 2.6 billion years old, they all trend in this sort of direction towards the center of the complex. I find this quite an interesting model, but it's not very widely cited or considered by the community, so surprisingly to me, I find this quite interesting. A little bit on geochemistry. The parent magmas now. I don't know, when should we do a short break, Melanie, after about an hour? Okay. A little bit on geochemistry now. This can be a little bit testing to some of the students when I talk about geochemistry. We look at the parent magmas now, and as I told you, this is based essentially on these fine-grained sills in the floor of the complex. These rocks, they have several groups of them, but perhaps if we just consider the main one related to the more primitive Bushveld rocks near the base of the intrusion, these are what we call silicious high magnesium basalts here. They have this curious sort of combination of very high silica contents, 56%, looks like an andesite almost in terms of silica, and then high magnesium, between 10 and 15% magnesium oxide. So very sort of, somewhat unexpected combination. There's also quite high chromium contents in these rocks. They have close to 1,000 ppm chromium and high nickel, 200-300 ppm nickel. And yet at the same time, they have high incompatible trace elements, such as the rare earth elements. There's 13 ppm lanthanum. That's very high. I don't know how familiar you are with typical lanthanum continents of mid-ocean ridge basalts. They have something like 1-2 ppm. So these are very high incompatible trace element contents, also zirconium. So this is sort of a very somewhat unusual combination of compatible and incompatible elements in these silicious high magnesium basalts. And I will explain in a little while that the main debate about the origin of these things is either we're melting some very metasomatized lithospheric mantle, or we have a strongly contaminated plume-derived basalts, magmas. This is, by the way, here data from a PhD project years ago by Ed Köhl at Monash, who looked at the mineralogy of these fine-grained sills in the floor. And you see they're essentially norites, fine-grained norites, micronorites that contain orthoparoxene, plagioclase, and small amounts, and much less clinoparoxene. So they're noritic rocks, broadly speaking. And the cumulates, of course, in the Bushveld complex are orthoparoxenites and norites, much more so than gabbros and bearlites and websterites. Okay, so I think we come to the PG in a little while to understand the PG. The other thing that's interesting about these magmas is they have very enriched isotopic signatures here for strontium and neodymium. I think I have show you a couple of diagrams now. In terms of strontium, this is the strontium isotopic profile across the intrusion here done by Kruger in the 1990s. And you can see there's quite a lot of variation, but if we first consider here the sort of the lowest value, initial strontium isotopic ratio is 0.705, and at 2.05 billion years ago, this 0.705 is around here. As you can see, this translates into a value that is significantly more radiogenic than the mantle Jur at that time. So that's essentially the story. The Bushveld magmas, even the least radiogenic Bushveld magmas, have a very, very enriched, strongly crustal signature. All of them that have been studied. So again, the possibility is either we're melting some lithospheric mantle that's been metasomatized sometime before mantle melting, or you strongly contaminate a crustal and a stenosphere-derived magma. The other thing that's important, perhaps, is that there's a lot of variation in isotopic ratio across the intrusion. Here, it's in general becomes much more crustal and enriched towards the top. So this suggests that the intrusion formed from several batches of magma. So I think that's the important point here. It's not just one intrusion that crystallized, one batch of magma that crystallized. Then there must be several batches of magma that are variably contaminated, probably already in some staging chamber. It's difficult to imagine how all this happened in situ here, these various crustal signatures and reversals that we see. So that's the strontium, and then here is the sort of summary of strontium isotopic signatures that I just, some mafic-ultramafic events across the globe, and as you can see there's Chur, there are some famous mafic-ultramafic intrusions here, there's the continental crust evolution from 3 billion years on, and you can see that the Bushveld here is really much more significantly crustal than the other mafic-ultramafic intrusions. It's at the same level as some of these anorthosites, but they of course are much younger, so it's really quite difficult to generate such very crustal signatures here for such an old intrusion as the Bushveld. So if this is really the result of crustal contamination, then it's massive amounts of crustal contamination, 30–40%. And people wonder, how is this possible? Such large degrees of contamination. We see the same thing in neodymium isotopes, so let's just skip this. If anybody is interested in this sort of thing, we can talk about it separately. What's also interesting is here, sorry for this busy diagram, but there's our low-polytic Bushveld complex. We have a small feeder-like intrusion of the same age, same lineature, same rock types, called Uitkomst here in the floor, about several kilometers in the floor of the Bushveld complex, sitting actually at the base of the Transvaal supergroup, dolomite and shale sequence here in orange and blue. There's the Archean basement in pink, and this already has very similar isotopic and trace element signatures as the Bushveld. So this tells us that this isotopic and trace element signature must have been acquired in a staging chamber, probably in the Archean basement granite. That's my feeling. Unless, of course, it's derived from a lithospheric mantle, metasomatized lithospheric mantle. So these are sort of the constraints we have at the moment. I think I skip osmium isotopes now for the moment. Don't know how interested you guys are in osmium isotopes. And by the way, I forgot to put the reference here for this diagram. This could be from Riceberg, Laurie Riceberg, possibly. Sorry for this, that I forgot the reference here. Yeah, and then in terms of lithophile trace elements, the spider patterns, the so-called spider patterns for here first shown for a number of continental flood basalts in southern Africa. There's this characteristic, enrichment trend towards the most incompatible elements, the negative niobium tantalum anomalies and titanium anomalies. These are very typical for continental flood basalts, and as you can see, Bushveld B1 magmas are very similar to these continental flood basalts. And here are some globally famous ones: Norilsk, Nadezhdinsky, Goldgate, Karoo, Tafelberg. That's the Etendeka, I think, in Namibia. And again, it's the same sort of signature. So the Bushveld magmas, in terms of isotopes and trace elements, that's the point here, are very enriched, similar to many continental flood basalts. And just like in continental flood basalts in the Bushveld, one of the main debates is this the melting of a metasomatized lithospheric mantle? This is a model that became very popular in the 70s and 80s. People like Hawksworth and others proposed this. Or is it a crustally contaminated asthenospheric magma? And still isn't resolved. I myself, changed opinion at least twice, backwards. And at the moment, I strongly believe, and I'll show you evidence in a little while for this, that these magmas are crustally contaminated asthenospheric magmas. But at some stage, I also was a follower of the lithospheric mantle model. And there I come actually to the reason here. Sorry for this. This is a trace element ratio diagram now, and this is a little bit complicated. We plot here more incompatible to compatible trace elements, lanthanum samarium, lanthanum niobium, for various sort of flood layered intrusions here. There is the Great Dyke and the Bushveld. The Great Dyke is in yellow, Bushveld in green. And one of the reasons why in the past I also adhered to this sort of idea that the Bushveld must be a lithospheric mantle, metasomatized lithospheric mantle magma, is that in the Great Dyke we have actually cumulus rocks that are both highly unenriched and therefore arguably derived from an astenospheric source, here these guys, and then we have very enriched cumulates with high lanthanum niobium and high lanthanum samarium that you could argue are either crustally contaminated or derived from lithospheric mantle. Okay, but in the Bushveld complex, until recently, we only had rocks here in green, samples that are strongly enriched. And so it was this sort of absence of rocks that could potentially represent the primary uncontaminated plume source that led people to believe, hey, this seems very strange. This whole stuff is derived from a metasomatized lithospheric mantle. And so I found this a credible argument. But recently, we actually managed to identify on a chilled margin of the Bushveld complex. I don't know how big this is going to show up here on this one. So yeah, reasonably. And there is a sort of a 1 meter, 1.5 meter sequence at the base, right at the base of the Bushveld complex at one locality here. These are sort of coarse-grained olivine pyroxenites. And then here is a meter-wide sequence of relatively fine-grained acicular pyroxenite that turns into an aphanitic glassy margin right here at the base, about 10-20 centimeters, 10-15 centimeters. And there is a sort of an element map of this material here. It's acicular textures of orthopyroxene in a glassy matrix. And that has 18.5% MgO. So this is of commodity composition, very primitive, unenriched in incompatible trace elements. So this is material that you would expect derived from a plume. This is impossible to generate by partial melting of a metasomatized lithospheric mantle. And so after all, we managed to find now an still potentially plume-derived component in the Bushveld complex. So I'm much more confident now that we might be looking here at a model like this. In other words, a plume-derived magma that undergoes crustal contamination in some feeder chamber and then is emplaced in the Bushveld complex here. So lots of contamination by the host rocks of the Transvaal supergroup that are dolomites mainly and pelitic shales. Good, and just a brief word on PG. I don't know how many people here at this university are interested in platinum group elements. I know that in Oulu they have quite a few. Just a word here on PG. Bushveld magmas. This diagram shows you our global database on platinum contents of liquids, of magmas, of melts, rather than cumulate rocks. And as you can see here, these would be komadiites at about 30% MgO. These are cumulates actually, 40% MgO, but these are komadiites, magnesium basalts, more differentiated basalts. And you can see that Pg contents platinum and palladium increase with differentiation in these magmas. Here, when you reach low magnesium contents, the Pg contents tend to fall. There are many samples now with low Pg contents. That's because the magmas reach sulfur saturation during differentiation. But in general, Pg contents are incompatible. They increase during fractionation. And when we look at Bushveld magmas here, they are at the upper end of the global spread. In fact, in platinum, they above the global data spread. This is another enigma that we don't understand. Bushveld magmas are very unusually platinum rich. This is really intriguing, and we have no explanation, so good explanation for this so far. I'll give you a couple of propositions in a sec. But so, this sort of fact that Bushveld magmas are unusually platinum rich relative to palladium, they have a platinum-palladium ratio larger than 1, is very unusual for global magmas. As you can see, the global magmas normally plot around 1. They have similar platinum to palladium. And this was another reason why people like this subcontinental lithospheric mantle derivation for these magmas, because that's the only mantle reservoir really that has such a high platinum-palladium ratio. And however, the other thing that's really, this is a diagram from Barnes et al. Recent paper in Lithos, where he compared global magmas in terms of a number of geochemical features. And these are platinum over titanium ratios here for global magmas. And you can see the Bushveld magmas are all these things here in with the red squares. And I think these blue triangles. So the point is that Bushveld magmas are really globally unique. really different from virtually all other magmas on the globe in terms of their PGE systematics. And so this is really difficult to understand for us, no matter what model you use. If the magmas are derived from the subcontinental lithospheric mantle and sucked out platinum and palladium perhaps from these lithospheric mantle rocks during ascent by some kind of a zone refining method, then you would expect other magmas on the globe surely to show the same thing. This cannot be, it's not a unique thing. Similarly, if the magmas are astenospheric and then have been contaminated by crust, perhaps by platinum-rich crust, okay, such platinum-rich crust exists. Some certain, black shales are quite platinum-rich, manganese nodules are platinum-rich, but that surely again should have happened in other magmas globally too. And it apparently didn't. The Bushveld really is quite unique. And so one of the possibilities I considered at some stages that if these magmas are plume-related, perhaps the Bushveld plume interacted with a portion of the astenospheric convecting mantle that was relatively platinum-rich. Why would it be platinum-rich? Why would such domains exist? Well, you're probably aware that our planet, the mantle, the Earth's mantle, after core formation, soon after the accretion of the planet, was refertilized by sort of a rain of asteroidal and meteoritic material, something called the late veneer or the late heavy accretion, and this sort of impactors reintroduced platinum group elements to the mantle, and it is possible that this sort of late veneer was incompletely homogenized with the mantle until 2 billion years ago, and thus perhaps the Bushveld plume interacted with one of these incompletely homogenized mantle portions, producing these unusually platinum-rich magmas. That's a possibility, but lots more work needs to be done to sort of constrain these models. So that was the first block of this lecture, introduction and brief look at emplacement models and a little bit on geophysics and geochemistry. Now what we're going to do is stratigraphy. I'm going to give you an introduction to stratigraphy based on lots of pictures of rocks. So this should be hopefully interesting to everybody. And then after that, we're looking at the ore deposits. So good. And let's continue with the second part now. This, by the way, is a picture not from the Bushveld complex, but from the Barberton Greenstone belt. But I put it in here because I like the school kids ripping us off. The geologists come to visit and they made fun of us. So that was out of safe distance. They were making fun of us. Right, stratigraphy and petrography. This first diagram is a little bit tedious because I briefly have to introduce here the stratigraphy to you guys. This intrusion is 8 kilometers thick. People subdivided it traditionally into 4 major zones here: lower, critical, main, and upper. When you go to layered intrusions globally, you often find this sort of subdivision scheme into a lower, an upper, a main or middle zone. And in the Bushveld, somewhat uniquely, they already introduced 100 years ago this term critical zone because it hosts all the ore minerals, the ore horizons, chromite and platinum group elements. And then the 5th zone, not shown here specifically in a lot of detail, is the marginal zone. That is sort of the contaminated or fine-grained gabbro-noritic contact zone that also is present in many layered intrusions globally. Okay, so what's also shown here is a sort of simplified version of Bowen's reaction series to tell the students what is to be expected in terms of a normal differentiating, fractionating basaltic magma body in terms of the rock succession. Bowen, of course, showed that the first mineral to crystallize is here olivine, and then followed by things like the pyroxenes and calcic plagioclase, spinel also appearing relatively early. And then, of course, the more sodic and plagioclases, the alkali feldspars, micas, amphiboles, quartz, and so on and so forth. So in terms of Bowen's reaction series, we would expect then in a typical closed system layered intrusion to have olivine-rich rocks such as danites and lerzulites at the base, and harzburgites overlain by pyroxenites, both clinopyroxene and orthopyroxene in many examples of layered intrusions globally, but in the Bushveld complex mainly orthopyroxenite, and then noritic or gabbronoritic or gabbroic rocks on top of that. In the Bushveld complex, these are mostly noritic here in the critical zone. And then when we come to the main zone in the Bushveld complex, we have actually gabbroic, clinopyroxene becomes important. So these are gabbroic rocks here, gabbronoritic, I should say, sorry, not gabbroic, gabbronoritic rocks in the main zone. And then in the upper zone, you begin to have rock types such as diorite, very important, diorites with lots of magnetite layers. And then right at the top, we even have a bit of granodiorite, highly differentiated granodioritic material. There's not a lot, there are a few tens of meters in places. So, you know, when you, strictly speaking, when you fractionate a basaltic magma right to the end, you should produce also a significant amount of granitic magma, but granitic rocks, but it's not a lot present in the Bushveld, there's just a little bit. So that's what we have. At the bottom, we have danites and orthopyroxenites here in the lower zone and lower part of the critical zone. Then we're getting into norites and orthopyroxenites interlayered with some anorthosite too. And then gabbronorite, much of the main zone is gabbronorite. And then up here diorite, diorite and still anorthosites. And then finally a little bit of granite. And in terms of the ore minerals, we have chromite layers in the lower portion. We have then sulfide horizons, sulfide-rich horizons here, forming the PG reefs. And then at the top, we have the massive magnetite layers, about 25 of those. So that, in a nutshell, is the stratigraphy. You can also see here in this diagram here the main phases appearing, newly appearing phases. So chromite comes in here, plagioclase, cumulus plagioclase comes in here, then clinopyroxene comes in here. And then magnetite up there. Then we have olivine reappearing up here, phyalitic olivine. There's a big gap here in olivine. The main zone is olivine poor, but there's phyalitic olivine appearing here. And then finally apatite. Apatite can be an important phase in some of these magnetite layers, and I'll talk about that a little bit later. So that's the stratigraphy in a nutshell. I'm briefly showing you pictures now of these different rock types here. Yeah, basal contact, mostly not exposed actually. There's just a few places where we show it. I showed you, where we can see it, I showed you this drill core intersection with a chilled margin, but that's very rare. Only in 2 places has the chilled margin intersected by drill core. That's because the mining companies don't usually drill, of course, into the floor of the intrusion. They drill at the ore horizons, which are located here further up, kilometer 2 above the basal margin usually. So we have only so far 2 drill core exposures of the contact, and elsewhere the contact is usually covered by vegetation and not well exposed, unfortunately. There are a few places, this is a picture from famous Cameron section, just a landscape picture where much of the work has been done in the 1960s by geologists from the US, Wisconsin, Eugene Cameron. He was the first really who did quantitative and detailed geochemical studies of the Bushveld complex, and he was of course a very eminent petrologist and very smart person, but he was also at the right time, the right guy at the right time, right place, because the early 60s, that's when microprobes, electron microprobes appeared, and in Wisconsin they had one of the first ones available to them, and so Eugene Cameron went to the Bushveld complex and did the first detailed mineral compositional profile across that intrusion. So until then, of course, it was wet chemistry, 10 analysis, if you're lucky, in a PhD thesis of 10 rocks were analyzed, something like that. So suddenly Eugene Cameron was able to produce here detailed mineral compositional profiles across the Bushveld, and these are still represent some of the type sections that we're looking at today. There is a nice profile here across the base of the Bushveld complex, the base in the lower portion of the Bushveld, in the eastern Bushveld complex, at Cameron section. So Eugene Cameron studied this profile here from, these are the floor rocks, this is Mahalisberg quartzite again, forming this prominent ridge here. And then further deep down, further back in the distance is actually the dolomitic country rocks underlying the Mahalisberg quartzite here. They are dolomitic rocks below that form these prominent ridges in the distance. And then the Bushveld complex itself, here's the context, you see, forms this sort of plain. These are the ultramafic olivine-rich rocks in the lowermost portion of the Bushveld complex that are relatively strongly weathered, and so a little bit more difficult to study. And this is the rocks, the contact actually comes back here towards us. This is another Mahalisberg quartzite outcrop. And then towards the road outcrop where I stand, it's right in contact actually with the, I'm right at the contact between the Bushveld and the quartzite. So you can see this is some kind of a trough here. The Bushveld complex forms sort of a trough-like depression in the country rocks. And it's, if you want, it's one of these things you see where these sort of, it forms these sort of troughs, and there's a kind of a swell or an up, a basement swell, and another trough here. So this is the prominent trough-like feature of the Bushveld complex called the Olifants River Trough. And so in this lower zone, in these olivine-rich lower zone rocks, you find these little pyramid-like hills, and these represent somewhat more resistant orthopyroxenite layers in a predominantly olivine-rich lower zone in this area. So these orthopyroxene little pyramid-shaped hills, you can see that they dip in this sort of direction, 20-30 degrees here towards the west, and that is the dip direction of the layers, and the dip of the layers of these orthopyroxenites. So there's another one here and another one here. So this is the interlayered olivine and orthopyroxene-rich sequence now of the lower zone going into the lower critical zone. And then here at the boundary between the lower and upper critical zone, that's where cumulus plagioclase comes in. So we're beginning to have norites here, right? And they are more difficult to erode. The norites form the sort of the topography, the hill. Much of this hill is norite. And then at the top of the hill, we begin to have in fact, all across this hill here, throughout the lower critical zone and the upper critical zone, we have chromatite layers. And then at the top of the hill here is a very prominent chromatite layer, the UG1 chromatite layer, and there's the first platinum-rich horizons just across the edge here, and a big platinum mine on the other side of that hill. So we're going towards the top of the upper critical zone, it's actually right about here. We have a profile here from the lower zone to the top of the critical zone. So when we look back at our profile, so this Cameron section goes right from the base here towards the top of the critical zone. The first 2 kilometers of the layered intrusion are covered in that profile. There's the contact here at where I stand for that picture, the road outcrop with some quartzite here. There's the quartzite in contact with the mafic-ultramafic orthopyroxenetic rocks. There's not a lot of alteration, as you wouldn't expect from a quartzite. The igneous rocks are quite unaltered. There's not a lot of evidence for contamination there. Elsewhere, however, we have here big blocks of dolomitic rocks in the basal rocks of the Bushveld complex. Also some quartzite here. There's a quartzite fragment in a sort of a fine-grained marginal rock. These dolomitic rocks in the contamination zone, they are quite interesting and important. People have done metamorphic studies of these to figure out at what depth the intrusion, this contamination event happened. They looked at the different metamorphic paragenesis and determined platinum temperature pressure relationships, and came up with a surprisingly shallow figure of something like, I think it was between up to about 3 kilometers of depth, which is interesting because that means here we are at the base of the Bushveld complex. When it was emplaced, it was only at a depth of 3 kilometers. Now, of course, the whole complex is 8 kilometers thick. So that would lend credence to the idea that the intrusion was in place as lots of small sills slowly inflating and building that complex. These sort of metamorphic studies of these dolomites. This was done by a guy called Thomas Wallmach in Pretoria. This is a typical example of a lower zone dunite here. So these little laminations, that's just a result of the polishing, sorry for that, but you have nice olivines here. The textures are very mature and equilibrated, triangle. So the sort of angles, the grain boundary angles are 120 degrees, so this is almost like a metamorphic texture. There's mostly olivine, a little bit of orthopyroxene here forming a big oikocrest in this area, but it's essentially a dunite. Not a lot of chromite in these dunites yet, so these dunites crystallized from magma that possibly were not chromite saturated yet. I think there may be a small chromite here, perhaps, and perhaps, yeah, but essentially not a lot of chromite at all. You get a lot of, yeah, and these are these sort of interlayered orthopyroxenite and dunite rocks that we have there at the contact between the lower and lower critical zones. There's lots of these white layers, you see, white layers and white veins. That is an alteration product of the olivine called berberite. And berberite is a term named after the North African nomadic tribe for a rock assemblage or mineral assemblage of magnesite, opaline silica. So these are alteration products really of the olivine, advanced alteration of olivine. First the olivine is transformed into serpentine and magnetite and then into magnesite and opaline silica. And so wherever you find in Africa or elsewhere, you know, on heavily weathered terrain, these sort of whitish blocks of berberite, that tells you we're walking on olivine, on terrain that is underlain by olivine-rich rocks. And so they form these veins and also these layers, these bedding parallel zones in these rocks. And in much of the critical zone, we have orthopyroxenites here. They have these distinctly foliated rocks that are now full of chromite, intercumulus chromite, disseminated chromite, not intercumulus, forming, you know, heavy disseminations here and often then massive seams. There's some intercumulus plagioclase in these rocks, typically a few percent. But this is a classical sort of typical orthopyroxenite from the Bushveld. Sorry for the colors, it looks slightly too thick, that slide, to me, because the orthopyroxenes are beginning to look a little bit orangey. Should be more grayish, so it's probably a little bit too thick. This is now the contact between the lower and upper critical zone. There's a prominent anorthosite, that's where cumulus plagioclase comes in, and several chromatite seams here. Altogether, there are 13 chromatite seams in the intrusion. Several of them are mined, not all of them. I explain it a little bit later why some of them are mined, why others not. Depends essentially on the chromium content of these layers. But these are literally very extensive, tens of kilometers. They can be up to about 1.5 meters thick, and they're mined for chromite at this place here. Very important, as you can see that here already, the contacts between the chromatite and the host rocks are knife sharp. And this is one of the big mysteries. How do you produce these knife sharp contacts? And this is one of the main criticisms of my, very early in this talk, I gave this model, you know, formation of cumulate rocks by raining down of crystals to the bottom of the magma chamber. This is difficult to understand, these knife sharp contacts between layers in terms of this model. And you can see that here already in this picture quite nicely. There is a close-up of one of these chromatite layers here. There is the contact actually between you see that first appearance of cumulus plagioclase forming this anorthosite here is a very prominent marker horizon throughout the complex. And here it is in close-up. And look how knife sharp the boundary is between the anorthosite and the pyroxenite, and then between the chromatite and the anorthosite, and the chromatite and the pyroxenite. Notice how many xenolith and otolith, really, rather than xenolith, occur in the chromatite. Notice this sort of little undulating, we call it egg box type texture at the contact. All these features are very difficult to understand with classical, you know, raining down of crystals to form cumulate rocks. I mean, it's really almost impossible to, you know, explain these sort of knife sharp. They're perfectly knife sharp contacts here. And that contact is actually defined by a little chromatite stringer, just about 1 millimeter thick, this undulating egg box type contact here. I think I have some details of this layer a little bit later. Then we have these, when you look at these anorthosites in thin section, they add cumulus, they're pure anorthosite almost in many cases. So again, how do you produce that? Plagioclase in petrology, if you remember igneous petrology, plagioclase usually crystallizes at eutectica with other minerals, either olivine or the pyroxenes or then quartz. So how do we produce pure anorthosites? It's one of the biggest mysteries still in petrology, in igneous petrology. You know, you have to separate the plagioclase crystals from the other co-crystallizing minerals. Some people propose you do that by flotation. Plagioclase is quite light, or perhaps by draining out of residual liquid from these anorthositic crystal mushes. But we really don't know. And Then we have also in the critical zone, the layering occurs not on just on the scale of meters to tens of meters, but also on the scale of millimeters to centimeters. Here is one of these layers of in an anorthosite. There's the anorthosite floor rock. There's a thin chromatite stringer here. Then comes orthopyroxenite, or actually, strictly speaking, when you look at model proportions, it's more like a gabbronorite or norite. And then it turns back into a leuconorite and an anorthosite. And people in the Bushveld complex call these things cyclic units. Cyclic units are units where we have a regular sort of repetition of first a high temperature mineral, such as chromite at the base, followed by slightly lower temperature mineral, pyroxene or olivine, and then moving into gabbronorite or norite, anorthosite, and then comes another very primitive high temperature layer, another chromatite. So this sort of alternation between chromite, harzburgite, pyroxenite, norite, anorthosite, chromite, harzburgite, norite, pyroxenite, norite, anorthosite, these are called cyclic units, and we see them on a scale of centimeters. And traditionally, cyclic units have been explained by magma replenishment to these intrusions, and I think increasingly we begin to realize that the situation is more complex than that. For a start, how do you generate a centimeter-wide layer that can be traced across kilometers and sometimes tens of kilometers? How can you explain that with a magma replenishment? It just doesn't really make much sense. So this, and there are also examples where the chromatite layer occurs actually on the top of one of these ultramafic layers here. So there is a harzburgite, strongly altered harzburgite with pyroxene and altered olivine, and then chromatite stringer at the top, and then anorthosite. So possibly these represent sill, the upper context of sill-like injections of some ultramafic crystal slurry. So we're beginning to think that these are much more common than we thought. Then in the upper critical zone, we have more typically what are norites in the Bushveld complex, but when you look at it in detail, often there's of course also quite a bit of clinopyroxene, but the orthopyroxene tends to be of cumulus nature, texturally earlier than the clinopyroxene. The clinopyroxene sort of fills the interstices between orthopyroxene and plagioclase and appears to be quite late. So in terms of terminology, this is a minefield actually when you look at terminology as it is used in practice by exploration companies across Africa and elsewhere in the world, I'm sure. You know, there is the IUGS terminology that simply looks at model proportions, in which case you would call this rock here a gabbronorite. It's about at least 20% clinopyroxene plus orthopyroxene and plagioclase. But in the Bushveld complex, traditionally the mining companies and many of the academics use sort of a genetic terminology whereby we only consider the cumulus minerals. And so in this case, this rock is called a norite. We ignore the clinopyroxene because it's intercumulus. And so, you know, when you look at the exploration reports and so on, and this very rarely is it explained then by the geologists whether they use this or this type of nomenclature. So this is a bit of a problem. So these are Bushveld norites or gabbronorites, depending on what you prefer. In the upper critical zone, we also locally have troctolites. They're not very common in the Bushveld troctolites, but they do occur in places. So there's some olivine, strongly anhedral in a plagioclase-rich matrix with these funny little inclusions of plagioclase. And people have pondered about these things too, whether they represent sort of, you know, inclusions of plagioclase floating around in the magma that are then entrapped by the crystallizing olivine. Come back to that perhaps later. And then towards the top of the upper critical zone, we have some key chromite horizons. I showed you earlier pictures that already we have chromatites here in the lower critical zone and at the contact between the upper and lower critical zone. But here now we're coming towards the top of the upper critical zone and we have some key horizons. The UG1, the upper group 1 chromatite, is a national monument in South Africa. It has this very characteristic interlayering in its floor rocks of chromite and anorthosite that people also have speculated for a long time about. And then above that, the uppermost is called the UG2, upper group 2 chromatite, and that is a very important layer because it hosts the world's largest platinum group element reserves. And when you look at this layer, I mean, you know, it's immediately apparent. What strikes you immediately is that this thing, well, let's look at it. What are the interesting things here? Firstly, the chromatite is underlain by anorthosite. This is an anorthosite. Its contact, again, is sort of undulating. We saw that already in some of the other layers on a much smaller scale, X-box type texture, I call it here. It's much larger scale, but it's still undulating. The chromatite is a meter thick. Then it has lots of sort of leader seams, we call them, thinner layers. Then comes pyroxenite, and then it's a knife-sharp contact here to leuconorite or northesite. So immediately when you look at this, you might think, okay, could this be a sill injected here into an anorthosite? So these are sort of the ideas that people are now beginning to be more favoring, rather than the classical, raining down of crystals, or perhaps even magma replenishment followed by raining down of crystals. So perhaps these things are all sills, injections of sills. What's this thing now? My mouse doesn't want to go down anymore. Interesting. I can still use it with my fingers. Okay, that's fine then. Yeah, I will use it with my fingers. So another thing that you have, I showed you just a moment ago this chromatite here and these sort of egg box type textures at the bottom. And they occur actually at all scales. Huh? We saw them a little bit earlier here, a few slides earlier in this. Here, in this diagram, you see on a scale of centimeters here. And I have some close-ups a little bit later. So it's very, very regular. And we see them here now in the UG2. On the scale of decimeters. And then when you zoom out a little bit, this here we form them on a scale of meters now. This is what we call a pothole in the Bushveld complex. And pothole represents a feature a transgressive feature where one of the ultramafic layers, typically a chromatite or an olivine or pyroxene-rich layer, sort of transgressively cuts down into an anorthosite or leuconorite. And there's an example of a chromite very sharply transgressing into a banded layered gabbronorite or leucogabbronorite. Here is the upper portion of one of these potholes. There's chromatite cutting down into its footwall, and then progressively the upper portion of that pothole is filled by pyroxenite again until just a meter above or so it's been back to normal orientation, flattened normal orientation. So these potholes, there is a picture of the same pit where these pictures were taken, the last two pictures. So this UG2 cross-section that we saw a moment ago is from the base here. There's the main seam. There's the top anorthosite here. So we looked at this sort of 10 meters thick, potentially sill-like body. And we looked at one of these deeper potholes now here in the face. So the mining company had an open pit there where we can get an idea about the 3D dimensions of these potholes, these so-called potholes or transgressions. And you can see they occur on any scale from a few millimeters to tens of meters. And in fact, in places in the Bushveld, they found potholes, transgressions that are kilometer wide and over 100 meters deep. So these things are very, very common. We increasingly realize they're common in other layered intrusions too. Bushveld, they've been known for a long time because we have the mining operations and exposure. Elsewhere they occur too. We begin to realize these things have been interpreted as sort of thermal-mechanical thermal-mechanical chemical erosion features. When new magma replenishes the magma chamber, spreads out on the top of the cumulus pile and sort of erodes down into the poorly consolidated noritic cumulates. That's the classical model. I think most people still would agree that this is largely correct. And so when we look at this now in a little bit more detail, you find them here are some close-ups. Typically, actually, when we go back to here now, you can see that this is the down dip direction here, and in many cases the potholes have a sort of a relatively steep up dip contact, and then the down dip contact tends to be shallower. It's not quite clear here, but in many cases this is what we see. Like here, there's the up dip contact here, very steep, and then much shallower in a down dip orientation. Many of them have pegmatoidal phases in the center. This is a pegmatoidal pyroxenite, which made people believe that there is perhaps some relatively volatile rich phase that contributes to the formation of potholes, exploits some weakness in the cumulate pile, residual volatiles are sent through the cumulate pile and sort of loosen it up and facilitate melting by new hot magma influxes. That's been a model. Then here you have a nice example where, a relatively larger one is surrounded by lots of centimeter scale potholes. The little black patches are really just centimeter wide potholes that are filled by chromite. The mining company has scraped off the chromite here from the top of the anorthosite quite easily. And so in the little potholes there's a little bit of chromite preserved. There you see another example. Sometimes they appear to be arranged maybe in the case of some kind of a channel-like feature, perhaps. Perhaps, these could be magma currents that move in a down-dip direction, eroding out these potholes. Sometimes we have the weirdest kind of star-like arrangement of the smaller potholes around the big ones, and nobody has any idea how these things might have formed. So, if you have any thoughts, let me know. Then also in the upper critical zone, there's a lot of other features that are very interesting. Traditionally the idea from the Bushveld complex is we have regular layering, and that is laterally very continuous. But when you look at it in detail, actually there's a lot of complexities. We see here, for example, lots of little fragments and schlieren of chromatites. So the chromatite layers are dismantled in places, actually in many places, and fragments of it and schlieren are dispersed throughout the upper critical zone. We have sort of schlieren and layers of ultramafic, mafic material intermingled with each other and locally forming little folds here. It appears that they are locally folded, you see. So schlieren of anorthositic and noritic, melanoritic material, both occurring. In many cases, it appears that wherever you have an orthositic schlieren, they are clearly associated and underlain by pyroxenetic schlieren. I think you can see this clearly here. Yeah. Clearly here or here. So in many cases, I see this or here. There's a pyroxenetic one below that, an orthosite. Here you see again features that perhaps look like folding, locally like folding here. Then we get these sort of balls or boulders, we call them, of pyroxenite and an orthosite. So lots of evidence for deformation, disturbance of the cumulate package, synmagmatic. We find this in other layered intrusions too here. You see this picture? Same thing, huh? These schlieren and fragments of ultramafic material here. You see, overlain by an orthositic schlieren. There's fragment, looks like an orthositic, but it's not an orthositic in this case. So here, a fragment of something lighter here in darker matrix. This is not from the Bushveld, this is actually from your layered intrusion up here in Zeeland, from Rainfjord. You got this picture from Marco Ilina, who worked with a group, I think, from Trondheim, in a mining company up in Rainfjord, in the Zeeland layered intrusion. So 500 million years or so old. Very interesting. And Zeeland is interesting for another reason, by the way. I attended a talk by a guy called Grant. I think he is a postdoc in Trondheim at a meeting not so long ago in Potsdam. And I learned from that talk that Zeeland also has a very unusually high platinum-palladium ratio compared to other layered intrusions globally. So I find this very interesting. Not that we understand why, but... Then there's another example of pothole here in the Bushveld complex. This time it's an orthositic pothole. So sometimes we realize increasingly potholes can be anorthositic, not just ultramafic. So there is our upper critical zone here with chromatite layers. There's the UG2 at the bottom. There are other chromatite layers. There are anorthosite layers in between. So this regular layered upper critical zone. And then there's a big pothole of anorthosite cutting down through it. You see, how on earth do you do that? I will propose a model to you guys, of course, soon. There are big fragments, you see, of the pyroxenetic host rocks floating around in an anorthosite. So this is quite quite interesting. When you look at the anorthosite actually in detail here, and this would be from this area here, this anorthosite layer, then you see features like this here, that the anorthosite clearly has cut up into the overlying chromatite, has intruded it. So it appears that, and also locally into the footwall, so it appears that this anorthosite was a relatively late phase, a late intrusion, intruding up and down, perhaps injecting into the semi-consolidated cumulate sequence. So that's something that totally sort of baffled us when we first realized these things and documented them. The anorthosites can be mobile perhaps, but how do you do this in an anorthosite? This is an adcumulate or certainly a mesocumulate, you know, stuff that in theory shouldn't be able to move anymore. We think that crystal mushes, once they have more than about 40% crystals, cannot move anymore. They're too viscous, too immobile. And so this field evidence suggests that the anorthosite here must have intruded. And if that is the case, then this cannot have intruded as an anorthosite. It must have intruded as a sort of a liquid mush of plagioclase pyroxene, followed perhaps by expulsion or draining away of residual iron-rich liquid, perhaps downwards back into the intrusion. All these questions. I'm beginning to struggle with my mouse here. It doesn't find this thing anymore. Maybe I have to get out of my thing here first. Okay, that's better. There's some more examples here from here. When you look at the anorthosite in detail, actually then locally you see it forms these little schlieren of pyroxenite or melanorite. They look lensoid, and this really looks like a deformed rock. It's like a metamorphosed or deformed rock. And here, other pictures from this big mega outcrop. There's the layered sequence with the chromatites there. The anorthosite, look how it intruded this host rock, this pyroxenitic host rock. So anorthosite clearly mobile in these examples. And then when you look at it in detail, it forms again these little schlieren and lenses. It forms these little cusps that all are oriented in one direction. To me, what these rocks are really, they are deformed in a probably synmagmatic state, and sort of mushes that are deformed. And here is you do chromatite again with a big elongated fragment of pyroxenite in it. They're very typical. They can be 5 meters long. And then another example here is an anorthositic fragment in the chromatite with a long elongated wispy tail. These things to me look like rocks that have been deformed in a mushy state. Yeah, I think we want to skip that. So the idea, the feeling that we have about these rocks is that it's some kind of a pull-apart structure. Here, the cumulate sequence was the whole intrusion dipped towards the center of the lopolith. During that the development of that dip of the lopolith, it was constantly replenished and continued to subside in the center. Portions of that layered sequence then, were extending and pulling apart, opening these gashes into which the anorthositic crystal mushes then could plunge down. That's how we imagine at the moment these sort of features to form. I think I'm going to skip that. Yeah, and there's another picture from the famous UG1 locality at Dwars River. You see here also chromatites. You see lots of evidence for synmagmatic deformation. There's a chromatite now being deformed and folded and forming lots of little stringers. And so to me what this looks like is there's this kind of a deformation plane here in this chromatite, in this anorthosite, along which this chromatite stringer was deformed and dismembered and fragmented. And this is from another layered intrusion, not Bushveld. It's one in Australia. We have the same kind of feature there, the schlieren of pyroxenite in an anorthosite or gabbronorite. So we have these in many other layered intrusions. We see these sort of evidence for synmagmatic deformation. This is an anorthosite in the Bushveld with nodules and little layers and schlieren orthopyroxenite. We call these things mottled anorthosites, so also suggesting some, and there are these boulders that I showed you earlier. We interpret them as broken up pyroxenite layers. And then there are these sort of features, again, egg box type contacts here, but this time at the upper contact of ultramafic layers. So they're sort of extending upwards into it, and we interpret these things as sills now. You see there's a thin chromatite that extends upwards into the overlying anorthosite. There appears to be some kind of a contact zone where the anorthosite is coarser grained and perhaps more felspathic. So I interpret this as a contact metamorphic feature following the intrusion of this ultramafic rock here. Okay, this is just a picture of some of these troctolithic hard-spogitic rocks we have in the upper critical zone. And now we're coming to the top of the upper critical zone, the Merensky Reef. This is Hans Merensky, the guy who in the 1920s discovered the mineralization together with some farmers in the Eastern Bushveld complex. He was a very, he's South Africa's most famous and most prominent geologist still today. He was another example, of course, of a guy who lived at the right time, at the right place. In the 1920s, 1910s, he discovered many of South Africa's important ore deposits, including the Phalaborwa carbonatite, the diamond deposits on the west coast, the chromite deposits, and the platinum deposits. And he's also in other regards a unique personality, because he was one of the, he died, when he died, of course, and being a very rich man, owning much of the Phalaborwa copper deposit and fertilizer phosphate deposit. He donated the entire deposit to the South African state up on his depth, and that's why he's still revered in South Africa. The Phalaborwa apatite deposit, very important for the South African economy, because during the apartheid days, South Africa was entirely dependent on internal fertilizer sources due to the blockade, the international blockade, trade blockade. Also part of the Bushveld event, of course, Phalaborwa. So the Merensky Reef, the horizon named after Hans Merensky here, is this layer. It's another cyclic unit, really, interpreted to represent a magma replenishment to the magma chamber of an ultramafic layer here, overlying a banded noritic anorthositic sequence. So you see nicely here these banded leuconorites with an orthositic sclerin in it, just like we saw before. And then comes this ultramafic horizon with the egg box type texture on a millimeter, centimeter, and even decimeter to meter scale. There it comes down again here, you see, on the right side. So these would all be potholes. It's really a transgressive horizon. And in detail, here you can also see the undulating nature of the basal contact. There's a chromatite seam at the basal contact, then comes typically a pegmatoidal layer, another chromatite, and then normally sized pyroxenite. And sulfide mineralization enriched in platinum occurs in the lowermost few decimeters, sometimes 20 centimeters, sometimes 50 centimeters here in this sort of interval. It's not a lot of sulfide, just 1, 2, 3, 4%, something like that. I have a couple of pictures here of this horizon. Oops, they come a little bit later when I look at the reefs in detail. I just briefly take you through the stratigraphy before we have another break. So then we come into the main zone. The main zone plateau here seen from, I'm standing in the critical zone. The main zone is a 2 kilometer thick horizon of relatively homogeneous gabbronorites. Here is a thin section of a gabbronorite with plagioclase, clinopyroxene, some orthopyroxene that in places is inverted pigeonite. It's medium grained to coarse grained, and really in many places, in many cases, relatively poorly layered. Locally we find layered horizons like this, but mostly the main zone is quite poorly layered. There is a prominent horizon towards the top of the main zone called the pyroxenite marker, where we may have some magma replenishment. And there we have these funny, when you look at it in detail, these funny sort of flame-like textures that occur at regular intervals. Here's another one here, you see? And then another one further in the distance here, where anorthosite intrudes, crosscuts through the layered banded melanorite pyroxenite. And there's a little extension of that flame going up here, and there too. So that again is evidence for the anorthosite injecting into the mafic-ultramafic horizon. So the anorthosites appear to be late, which is really quite interesting. And then the upper zone, we're almost done before we have another break. So we looked at the main zone now here. You see? And in terms of the strontium isotopic profile, there was the pyroxenite layer that we just looked at. And it's a marked reversal in terms of strontium isotopes and also magnesium number. This is the magnesium number profile across the sequence from the main zone, pyroxenite layer, upper zone. So there's a reversal towards more primitive compositions here. And the strontium isotopes become less enriched in this pyroxenite marker. So this sort of horizon appears to represent a major magma replenishment to the Bushveld complex. So we see that here. And then the upper zone, the remainder of the complex here, another 1.5 kilometers, is very enriched, of course, in about 20 massive magnetite layers. You see them here, sort of schematically, little lines. And these host 80% of the world's vanadium resources. So they're very, very important. They up to 1.5 meters thick. This is the main magnetite layer here. It forms a dip slope. It's dipping about 15 degrees towards us. 1.5 meters thick magnetite layer. We walk on the pavement here. There's a close-up of one of these magnetite layers. There are about 25 of them. This is a thinner one, also vanadium rich. They don't mine it because it's not thick enough. But you can nicely see the knife-sharp contact, lower contact. In many cases, they also have knife-sharp upper contacts. Here's great gradational into an anorthosite. Okay, so let's have another 5-minute break, I'd say, before we look at the platinum group element reefs. So I hope the stratigraphic portion was not too boring, tedious. It is hard sometimes. Sure.
Can I just ask one thing? When you were showing these, like the lobes of the anorthosites into the overlying, like chromite layer or something like that. I know that in the people working on like flood basalts and things like this, they interpret very often these like undulation of the boundaries between two different like portions of the magmas. Like the gravitational instabilities, especially in this case, if you would have the upper layer, which is more dense than the one that is underneath, it will actually create, the instabilities with a certain wavelength, and then it will, facilitate the movement of the lower, less dense magma into the upper part.
Yes.
In some cases, it was actually reversed, so it was hard for me to understand it. But I just, recently heard some talk about people, talking about features like this.
Yes, yeah, I agree. The problem is, of course, that the melanorite here is very nicely banded and regularly banded, not deformed at all. It seems to be some kind of a cross-cutting, actually, that the anorthosite cross-cuts it. So to me, this means that the melanorite was already solidified, largely solidified when the anorthosite injected.
Yes, you don't see like a banding of the anorthosite around.
So I think we increasingly believe that the anorthosites are quite late and mobilized, actually. And actually, I think I showed another picture from the main zone. Was it this one here? When you look at that in detail, you also see actually, you can see that, you see here, we're looking at this close-up of this picture here. Here are the anorthosite bands, layers, and the anorthosite is beginning to be mobilized in this area here, you see. There's anorthosite veins moving upwards into this is a little zone of brecciation and deformation here in the layering sequence. And the anorthosite is quite mobile at the end. So it seems increasingly that the anorthosites are relatively late crystallizing rocks. So how this is possible, what that really means, I mean, if this is an anorthosite, a pure anorthosite, it must have lost, after emplacement, it must have lost residual liquid, because it cannot move like this as a pure anorthosite. There is no pure feldspathic liquid. No, cannot be, I think. And so it must have lost some residual liquid. Good. So I have about 1.5 hours or so to finish this, and we're looking at ore deposits now, and I have to speed up a little bit, not to get lost here too much in chatting. History of discovery and mining. This started round about, the deposits were discovered actually in 1924 when Hans Morensky was sent a sample, a number of small nuggets of silvery material that he identified as platinum from a farmer in the Eastern Bushveld complex on the farm Maandagshoek. But quite interestingly, actually, already for about 15 years before the actual discovery, there was rumors in South Africa of platinum, the area being prospective for platinum. And I think that's important, you know. In exploration, this is commonly like this. I mean, it's not out of the blue that suddenly people realize there is prospectivity for a certain metal. I mean, people have found sniffs and little indication and so on and so forth. And Morensky would have been aware of these rumors and these reports in the past. For people, for example, in 1908, people panned in the Pretoria area some platinum. They were hydrothermal, actually, interestingly enough. Hydrothermal platinum deposits are very rare. Platinum and palladium appear to be quite immobile metals, but there are a few rare examples of hydrothermal platinum lodes, and associated with the Bushveld there is the so-called Waterberg lodes. A couple of papers have been written on those. They're mega rich in platinum, several tens of grams per ton, platinum only, interestingly enough, not palladium, associated with some rare earth element rich mineralization and quartzite in the roof rocks of the Bushveld complex, suggesting, of course, that platinum ultimately comes from the Bushveld at depth. But we don't understand yet how the platinum was mineralized, how the platinum was mobilized and transported yet. So, because these deposits are so rare, relatively little research is done on hydrothermal platinum deposits. In 1928, then, the first mines were opened here in the Rustenburg area in the Western Bushveld complex, and so on and so forth. And then these were all underground mines here. A history of, 70, 60 years of underground mining until in 1991 here at Mokalakwena in the northern lobe, the world's largest open pit platinum mine was opened. And now recent discoveries here in the northern lobe, the so-called flat reef. I will show you in a moment what that is. And so, long history of exploration and mining in the Bushveld complex. All right, so we look at, I think I show you just one phase diagram that I will use on many of my slides now. It looks complicated, but it's relatively simple actually. I'll take you through it briefly. So what we're plotting here is the sulfur content of Bushveld magmas, or of magmas in general, against the weight percent crystallized, the percent crystallized of a magma. And up here are the different MgO contents that the magma has at these stages of crystallization. So from 10% to 50-60% crystallization here, you can see that in the first, and this is for a model basaltic magma. We did these calculations here, and so you can see, starting at about 14% MgO, you can see during the first 10% or so of crystallization of a basalt, we have olivine mainly crystallizing, then orthopyroxene here, and then orthopyroxene and spinel, chrome spinel, and then finally here gabbroic rocks, gabbronoritic rocks, where orthopyroxene, spinel, and plagioclase crystallize together from about 5% onwards, 5.5% MgO onwards, and then finally here gabbronorites. So the point is that typical basaltic magmas, when they are placed into the crust, they strongly undersaturated in sulfur. That is because the magma, when it's formed in the mantle, the partial melt of the mantle, may be sulfur saturated in the mantle, but during ascent through the lithosphere, sulfur saturation, sulfur solubility is going up significantly. The sulfur solubility of a magma increases with falling pressure, so that when the magma then is placed here into the crust, after 200 kilometers of traverse through the lithosphere, it is strongly sulfur undersaturated. And so Bushveld magma has about 500 parts per million sulfur, whereas the solubility of sulfur of Bushveld magma at atmospheric conditions or subatmospheric conditions is on the order of 1500 ppm. Okay, So that is very good because most basaltic magmas, when they're placed into the crust, are sulfur undersaturated, therefore. And so then what happens during continued fractionation here of the basaltic magma, crystallizing these various phases, olivine, orthopyroxene, plagioclase, and so on, the temperature, the magnesium content goes down, but the sulfur content goes up. Okay, because sulfur is not incorporated into olivine, pyroxene, plagioclase. And at some stage, of course, the sulfur content goes up. The sulfur content of the magma goes down. Sorry, this is so difficult to look at this place here. The sulfur content of the magma goes up, but the MgO content, the sulfur solubility of the magma goes down, sorry. Yes, and the reason for the sulfur solubility of the magma going down here is a temperature effect and an iron content effect. The temperature effect is relatively easy to understand. We are all kind of familiar with this. When you put a lot of sugar in a coffee, in a hot coffee, you let it cool down. If it's really a lot of sugar, then the sugar will precipitate at some stage. So, you know, the solubility is dependent on temperature. And it's similar in a way in magmas. The sulfur content and sulfur solubility, here the sulfur solubility essentially of a magma decreases with falling temperature or increasing degree of crystallization from the left to the right. And so temperature effect, but also an iron content effect. The iron content of that magma decreases from left to the right because olivine and pyroxene are iron rich, and if you fractionate them, the magma becomes more and more iron depleted. So, and sulfur bonds to iron in the magma, and if you take away the iron from the magma, sulfur loses its bonding partner, so it becomes less and less soluble. So sulfur solubility decreases, sulfur content of the magma goes up during crystallization. At some stage the two will meet and the magma reaches sulfur saturation, right? So this happens in the case of the Bushveld magmas round about when plagioclase appears on the liquidus. This is important because that is really what we see in the intrusion, very schematically shown here. Here are the PG sulfide reefs. They occur near the contact between the pyrogenetic ultramafic portion of the intrusion and the gabbronoritic, predominantly gabbronoritic portion of the intrusion, round about that horizon where you would expect them to occur, right? This sort of geochemical modeling comes up with a result that is broadly to be or matched in the field evidence when we look at the rocks, the location of the reefs. And I think I'm going to skip this thing here, that's important. So I'm going to show you this diagram now when we look through the different reefs now several times. The other thing that's quite interesting, the red line here, is actually the nickel content of a fractionating magma. And starting, you know, many primitive basalts have on the order of about 1,000. This is just schematically here, the nickel content, by the way, have on the order of about 500 ppm nickel. So sorry, ignore this x-axis, this y-axis here. These values, of course, are for the sulfur content. But primitive magmas are rich in nickel, and the nickel decreases then relatively rapidly during early crystallization of olivine, because that's where the olivine, that's the main phase accommodating nickel. And then it decreases somewhat less rapidly here when orthopyroxene crystallizes, and then once plagioclase joins the assemblage here, the nickel content of the magma remains quite stable. The point here being is that nickel content of magmas decrease rapidly during fractionation, and if we want to generate nickel-rich sulfide deposit, then we need to drive this magma relatively early to sulfur saturation so that the sulfides can be nickel-rich, right? The problem being that many primitive magmas are quite sulfur undersaturated here, you see? So to do this, to form nickel-rich sulfides in magmas, we normally need to bring this magma to sulfur saturation here, we need to add external sulfur, quite substantial external sulfur, by means of contamination. And so this is why many magmatic nickel sulfide deposits show lots of evidence for contamination. If you wait too long, you know, of course, we reach sulfur saturation here, but the nickel content of the magma now is relatively low, so these sulfides are not particularly nickel rich anymore. That's just as an aside. Okay, so what I'm going to take you now is I'm going to take you briefly through these different types of mineralization. There are the chromatites here, and then we look at the PG mineralization, and then also the magnetites right at the end. Right at the base of the complex, actually, and somewhere here in the lower zone, there is a somewhat unusual horizon of local contamination where the magma reached sulfur saturation. And this is not economic at the moment, it's not being mined, but as you can see here, this is a horizon of about 30-40 meters of elevated PG content, several grams per ton, perhaps on average between 2 and 3 grams per ton. So this is potentially mineable in a large open pit operation. Not at the moment at current PG prices, but sometime in the future, quite feasibly, quite possibly mineable. This is a common story, of course, in ore deposits, you know. Interesting when you think about how all our resource and reserve estimates that we have at the moment for how long our metal resources on Earth still last, of course, do not take into consideration these sort of sub-economic and marginal deposits of which there is a huge amount of and which may become economic as soon as the prices will rise slightly, which is to be expected once our resources become scarcer. So this is sort of an example why these sort of predictions of of our estimates of available resources are to be treated with a lot of caution. Many of these, in the Bushveld, we have many of these deposits that are currently sub-economic, but that might be economic at some stage in the future. Okay, so a lot of PG here in this horizon. If you would compress that into just, instead of 30-40 meters, into just 5 meters, then it would be very, very economic. And the total amount of PG that is down here in the lower zone already is higher than that in the Morensky and UG2 chromatite, the world-class deposits that we have further up in the intrusion. It's just not concentrated enough. And that is a theme I come back later to, that, you know, the key factor is how do we concentrate the mineralization in narrow horizons? And that, of course, is the main thing that people have been struggling and trying to explain for the last decades. These are the rocks that this deposit occurs in. These are hardspokites and pyroxenites. You see the sulfides here, a few percent, not a hell of a lot, just a few percent sulfide. That's what this mineralization is hosted in. Okay, so that was this deposit down here. And the magma here at this stage is still quite primitive. We have only olivine and orthopyroxene forming, hardspokites, pyroxenites. So we're somewhere here in terms of sulfur solubility, quite high. Our sulfur content of the magma is still quite low. So how on earth do we generate sulfur saturation at this horizon down there in the Bushveld complex? It has to be contamination. Okay, that we add some external sulfur to the magma to reach locally sulfur saturation. And at this horizon, in fact, at this ore horizon, there's a numerous xenolith of country rock material suggesting that that's what happened actually. So it's probably a localized, relatively localized, isolated feature of magma contamination that led to this mineralization here. We have no other place in the Bushveld lower zone where we see this type of mineralization. But there are globally other, in a sort of a survey of layered intrusions globally, I listed here a number of other intrusions where we have mineralization, PG mineralization already in the lower zone, the ultramafic rocks. As I said, based on this diagram here, it's a relatively rare thing. None of them really is economic. And this is because, you know, we are here at a position still during magma evolution where we normally have relatively high sulfur solubilities and low sulfur contents. So this is, I think this is important to understand that in the primitive portions of layered intrusions here, the very ultramafic portions, they tend to be quite poor in sulfide mineralization because of these sort of features. I hope you all understood this sort of diagram, the rationale behind this. All right. So then we look at the PG and the chromatite seams. Now we're going a little bit further up here in the intrusion. We are now here in these in the critical zone, lower and upper critical zone. We have numerous chromatites, and all of these chromatites got actually elevated PG contents. And this is another thing that petrologists haven't completely understood yet why this is so. So I'm going to look at some of these now with you. There are some pictures of these chromatites. There is one of the LG lower group chromatites, number 6. It's mined for chromite, also not for PGE, but for chromite. There are some of the middle group chromatites, the upper group or UG1 chromatite, another middle group chromatite. So you see here a number of these features of these chromatites. When you look at them in detail, you can see that they're quite complex. They have lots of otolith here of anorthosite, pyroxenite, norite, pegmatoidal, finer grained. So very complex features suggesting that they're actually quite dynamic, quite dynamic emplacement mechanisms. And then you have, portions of the chromatite seam where the chromite is much denser packed, like here, and then much looser packed surrounding that. And this portion is even looser packed than this one. So they're quite complex, actually, in detail when you look at them. And in other cases, you see lots of little otolith of plagioclase here in that chromatite stringer. Lots of branching out and bifurcations. So very enigmatic. And people have suggested in the past, including myself, that perhaps these things are injections of chromite into the cumulate pile. You might imagine, that these things then are really leftover fragments or portions of the original of the host rock here, and the host rocks being anorthosite and pyroxenites on top of it. Maybe these are fragments of the host rocks that have kind of survived when the chromatite slurry injected into this thing. Again, look at the elongation of many of the otolith and their wispy tails. So this is important when you look at models of emplacement of these slurries. I think what it means to me is that the emplacement if these chromatites were emplaced as a slurry, then it wasn't extremely turbulent, because these wispy tails would not have survived in a kind of density current like rush running down a magma chamber, like at continental margins. Turbulent currents. It must have been much more gentle, perhaps laminar, and slowly emplaced these mushes to survive all these highly elongated and wispy inclusions, otolith. Some other pictures, there's UGs now, we saw that. Sometimes they're forming these almost dike-like potholes here. There are examples of these highly elongated xenolith in these chromatites, you see, several decimeters to meters long. Again, how these things could not have survived if these chromatites, some people have suggested that layered intrusions formed by turbidity currents along the walls of the intrusions, rushing down like very fast and then spreading out at the bottom of the intrusion. But these sort of features, these meter-long otolith here of pyroxenite could not have survived these sort of turbulent currents, of course. So it must be a much more gentle and slow mechanism of slurry emplacement if indeed these things were emplaced as mushes and slurries. And this is how the seams actually look like under the microscope. This is the proportion of gangue here. You see many of them got about 5 to 10 to 20% gangue material, silicate material, but some of the upper chromatites have 40-50% silicate material. We saw that in one of the previous examples, the MG. This example, you can see there's a lot of intercumulus plagioclase in here, in this chromatite seam. So that's how they look under the microscope. This is a little bit on their chemistry here, the chrome-iron ratio. That's important for the people who mine chromite for the steel industry. Chromium is a very important additive to steel, to make steel harder. And so we are interested in very high chrome-iron ratio in the chromite crystals. And the highest chrome-iron ratios here are found in the LG seams, the lower group seams. This is the lowermost seam, the uppermost seam. We group them into lower group, middle group, and upper group seams. So good chrome-iron ratios here in some of the lower group seams, but these are quite thin. As you can see, the ones that they mine, here's the LG6. It's about 1 meter thick. Chrome-iron ratio is not so good anymore, but it's acceptable. And then they mine sometimes here one of the MGs. The MG2 or even the MG4. The MG4 is quite thick, but has not such a good chrome-iron ratio anymore. The UGs, they don't mine for chromite. The chrome-iron ratio is getting too low to be economic, but those, of course, are increasingly rich in PGE when we go with height. Okay, so these are the ones that they mine. that's all about. So the important thing is, broadly speaking, the chrome-iron ratio decreases with height. They become more and more differentiated, as would be expected. Chrome is very compatible into chromite, so the chrome-iron ratio decreases when you go up in the sequence. So in exploration, that's important. When you know, in a large layered intrusion that is prospective, not just for PG and sulfides, but also for chromite and magnetite. If you're interested in chromite, you need to find the lowermost of the chromatite seams to make any money. And this also is interesting when we look at chemi in a moment, towards the end of the lecture, the one in Finland, because that I will show you that's quite differentiated actually. Origin of the chromatite layers, well, a lot of debate about this. Number of models here. The original ones were, people like Wager and Brown suggested that the dense chromite crystals were preferentially settling and sinking faster than the other silicate minerals and accumulating at the bottom of the intrusion. We now know this cannot be that simple. There are a number of problems with this. Firstly, the chromite crystals probably are so small that they have a very low ability to sink through relatively viscous silicate magma. That sort of yield strength is quite high. Also, how do you explain the knife-sharp contacts between the layers that I showed you so many times now? You know, if chromite crystals really gently sink down, then you should have very, very progressive and gentle contacts, transitional contacts between layers. And almost always we have knife-sharp contacts. So this does not really work. Things like change in oxygen fugacity, contamination essentially of the magma. If we suddenly change the oxygen fugacity of the magma, then chromite may become insoluble, contaminated with some pelitic rock that is strongly reducing. So that might, that is strongly oxidizing, that might trigger chromite precipitation. Change in pressure, some people have looked at that. Not a lot of support for that, I think. Crustal contamination with silica, another thing. So not just oxygen fugacity, other components also affect chromite stability in magmas, of course. Magma mixing. You know, people have shown that the stability, that the liquidus of the chromite in phase diagrams is curved, like almost every liquidus surface is. And so if you mix primitive and differentiated magmas, you may end up in the superliquidus field of the chromite. But again, even if we do that, how again do we explain these knife-sharp contacts between seams? That's always a big problem. And then some people have proposed that perhaps chromite crystals, chromite slurries were already entrained from some staging chamber as some crystal mush into the intrusions. Lots of models, but we essentially are not sure yet what's happening. This is a summary of chromite contents actually in global lavas from komadiites here. Here, these are about komadiites, then towards basalts. And as you can see, most komadiites here, these are cumulate rocks actually. And then into komadiites here, they have a trend of increasing chromium contents with fractionation. So that tells us the chromium is undersaturated in most komadiites, the primitive komadiites, until chromium or chromite reaches saturation here at about 20-25% MgO, and from then on the chromium content of magmas decreases quite rapidly. That means chromite is now saturated. So it's about 20-25% that komadiites reach chromite saturation. So the point here being is that chromite is a phase that in really primitive magmas actually reaches saturation after olivine. So the olivine is the first phase in Bowen's reaction series that starts crystallizing, and then chromite joins a little bit later. That explains why in many layered intrusions the primitive, really ultramafic, danitic lower portions are relatively lack massive chromatite seams and often are very chromite poor. All right, so we are here now in our schematic model of a layered intrusion, the chromatite seams. Where are we in terms of our sort of sulfur solubility diagram? We are still somewhere here. You see, spinel has started to crystallize together with orthopyroxene. That's the point. Spinel also normally forms a eutectica with other crystals. So to form a massive chromatite seam, you need to separate it from the pyroxene. That's the big problem. So we're somewhere here now. Still, the magma should be sulfur undersaturated quite strongly. So yet we have sulfide mineralization, and most of the chromatite seams got a little bit of sulfide. So this is again something that's not so easy to understand, and it's possible, you know, that already the magma locally was reached a relatively differentiated stage, so that sulfides could start to segregate, whereas the overlying and underlying rocks were, you know, more primitive then. So basically, we are approaching slowly the point at which sulfides can begin to segregate. But strictly speaking, we are still a little bit too primitive. So therefore, the mineralization, the sulfide mineralization that we find in most chromatite seams is quite minor. I think I'm going to skip this. So when we look at the PGE contents of chromatite seams, this is a summary of Teigler from the 1990s, his PhD thesis. You see there the lower group seams, middle group and upper group seams. So the lower group seams are quite PGE poor, but still there is more PGE than you would expect from just the trapped basaltic magma between the chromite crystals. So already a little bit of sulfide saturation in the lower seams, but in general the PGE contents of the chromatites increase with height. Again, in exploration that is important, and we see it in other layered intrusions too. What that tells us is that when you look for PGE seams, purely from a sort of a, you know, an exploration point of view, an observational feature is that the PGE contents increase. Therefore, if you're going for a PGE reef, it should be, you know, it's unlikely that you find a good PGE reef near the base of a layered intrusion. Whereas in the case of chromatites, we're looking for the lowermost chromatite seams. In the case of the PGE, the uppermost chromatite seams are the target. Why this precisely is so in the case of the PGE remains an open question. I think we'll maybe touch on this in a little while again. Why are chromatite layers PGE rich? Here's a traditional model. Sulfides and chromite precipitate together, perhaps due to fractionation. So let's go back to this diagram. Yeah. Oops, sorry. So we are somewhere here in the field where orthopyroxene and chromite crystallize together, but remember the Mg chromatites and the Ug chromatites are underlined by anorthosite. So we are closer to this boundary here where plagioclase becomes a stable phase. So close to the point where sulfur content of the magma is high enough now and sulfur solubility is low enough so that we begin to reach sulfur saturation, okay? So this might explain why in the lowermost chromatites of the critical zone, the ones that are more primitive, sulfur, probably less sulfur content of the magma, higher sulfur solubility, we have much lower PGE contents than up here in the chromatites that are underlain by anorthosites. So the first anorthosite underlain chromatite here is the Mg3 and Mg4, and you begin to see much higher PGE contents now slowly here. And the Ug1 and Ug2 are associated with anorthositic footwalls. So this is probably the reason that these magmas become more fractionated now and closer to sulfur saturation. So sulfides and chromite precipitate together due to fractionation. And then why are this explains the PGE content of the chromites, but they're very sulfur poor. Most chromatites have so little sulfide that we can't identify it, can't see it in hand specimen. What is the reason for that? People argue that after precipitation of sulfide, magmatic sulfide together with chromite, some of this sulfur of the sulfide or much of the sulfur in the sulfide was mobilized by late magmatic fluids and transporting and mobilizing that sulfur up into the overlying convecting magma chamber. And here's a study by Perry Goidova and Sarah Jane Barnes in 2002. They showed that when the sulfides, the magmatic sulfides, lose some sulfur due to the interaction with these late magmatic fluids, they may undergo partial melting, and copper and palladium go into this partial sulfide liquid, and the ruthenium, iridium, osmium, and platinum stay behind, forming alloys commonly. So that explains then the relatively PGE but sulfur poor nature of many of the chromatites. There is a late magmatic reaction of these magmatic sulfides with some residual volatile rich fluids. Good. Again, we're looking at these potholes. I showed you, of course, these potholes before. that are characteristic of many of these chromatites. Oops, sorry. And the reason this is very important, these potholes, because I mentioned earlier that people think that these potholes formed as a result of magma replenishment. Replenishment of the magma chamber with very hot primitive magma eroding down and transgressively eroding down into the underlying felspathic rocks. And it is so these sort of features tell us that the magma chamber was replenished with and refertilized with PGE. And this explains why, when you look at the different chromatites here, why we still have PGE in the magma chamber after the formation of the first chromatites. So the magma chamber was constantly replenished, refertilized with PGE, as indicated by for example, the formation of these potholes, these transgressions that we believe are the result of these replenishments. So, if this is correct, then really those magma chambers, those layered intrusions that are the most dynamic, most replenished, are the prime targets for PGE reefs. I showed some of these slides earlier, examples of the Mariinsky Reef. We have here again this horizon that is considered to be the result of a magma replenishment, sitting on top of an anorthosite here, a chromatite, some pegmatoidal layer, an orthopyroxenite, pegmatoid, another chromatite, more orthopyroxenite. A couple of slides here. There is our melanoritic floor overlain by an orthosite layer. So sometimes this anorthosite here that is underlying the Mariinsky Reef is quite thin. Almost always there, but it can be thinner or thicker. There is our Mariinsky pegmatoid and the normal textured pyroxenite, and a couple of other examples here. There is the anorthosite, basal chromatite. Sometimes the chromatites combine to form a single chromatite. There's the medium-grained pyroxenite. There's the pegmatoid. Here's a beautiful example from the internet where pegmatoid, basal chromatite layer, very thin in this case, pegmatoid, and then upper normal grain pyroxenite. Or in many cases, you see the anorthosite immediately underlaying forms a sort of a band of pure anorthosite, almost like a reaction zone. So this is quite interesting. Here is another example: anorthosite or leuconorite, chromatite, basal chromatite, pegmatoid, and then upper chromatite somewhere here, and medium-grained pyroxenite. Sulfides concentrated in the pegmatoid and associated with the two chromatite stringers. And again, you can see here the undulating egg box type nature of the contact, and there is a pure anorthosite corona or halo in the immediate floor rocks. And there are people who feel, that this cannot be a coincidence, that the formation of this anorthosite here and the chromatite stringers and the pegmatoid is related to some late magmatic fluxing by volatiles, triggering partial melting of a protocumulate and concentration then of sulfides during this process. So this is a possibility. I think I'll come back to this a little bit later. There's another example from underground now. Here is a norite, leuconorite, in this case a bit troctolytic here. There is our chromatite, basal chromatite stringer, centimeter 2 or 3. In this case, it's not very pegmatoidal above it, but it's a sort of medium-grained pyroxenite. But look at this beautiful undulating nature, and the pure anorthosite again forming a sort of a zone immediately below the reef, suggesting some reaction feature to my mind. So differences to the UG2, to the chromite-hosted mineralization is here. We still have chromite associated with the main peak mineralization, but the chromatite now is much thinner. Of course, there is more sulfides in the Mariinsky Reef than in most of the chromatites. And of course, we're stratigraphically a little bit higher than the chromatite seams. But broadly speaking, lots of similarities. In detail here, I think I'm going to just skip this in the interest of time. Here are examples of other Mariinsky-style mineralizations. This is in a paper from 2005 in the African Journal of Earth Sciences. And examples globally of reefs, PGE reefs, similar of the Mariinsky Reef. There's one in Finland here, or two in Finland, and a number of examples globally. So if anybody's interested, that's where you can look. And yeah. So stratigraphically speaking, we're right here now between the essentially at the top of the upper critical zone, below the main zone. And so in terms of our diagram here, we're sitting up here. In terms of our phase diagram, we're sitting right here now where plagioclase starts coming in, or just above that horizon. The first plagioclase horizons and orthosite horizons started coming in here. So we are in the area where we expect the magma to reach sulfur saturation. The key problem is, how do we concentrate the sulfides into an economically mineable horizon? Because you can do simple mass balance to calculate how much sulfide would actually crystallize here from the magma cotectically, and it's about between 1/4 and 0.5% of sulfide in our cumulate rock would be expected. And in the reef, we find 2, 3, 4%. So there is some concentration here that we need in addition to just precipitating sulfides from the magma at this point. And the key question for all petrologists is, how do we concentrate this sulfide in these reefs? And I think that's the key question that I want to answer here. Now, when you look globally at the distribution of the main PG reefs in layered intrusions, that is, chromatites and also Merensky reef style, they always occur near the contact between the ultramafic and the mafic complex. When you look at Bushveld here, we had the lower and lower critical zone that is just pure ultramafic rocks. Then we had the interlayered mafic-ultramafic rocks of the upper critical zone with UG2 chromatites somewhere here, some of the MG chromatites here, and then Merensky reef, and there's the main zone. In other layered intrusions like Great Dyke, it's right at the contact. They don't have this sort of interlayered mafic-ultramafic zone, they just have ultramafic zone and then a thick mafic zone. Same here, Muni, Winterlina Hills, Stillwater, it's always near that horizon in that sort of transition zone between ultramafic and mafic rocks. And that can be explained by, is it coming again? No, it's not coming again. Yeah. That can be explained by this diagram. We're sitting somewhere here now. That's why we have the main PG reefs in these layered intrusions. So from an exploration point of view, that's very important to remember that this is our target horizon. When you're in a layered intrusion somewhere in the Siberia or the Congo or the Amazon jungle, and you're finding interlayered ultramafic rocks, danite and peridotite, your task is then to figure out what's up and down. That can be quite tricky. And then you have to go up. Okay, you move out of the predominantly ultramafic zone. You have to get higher up until where you begin to have gabbroic noridic rocks. That's your main target horizon. So quite simple principles, I guess, but in the field, of course, the task is considerable to figure out what's up and down, particularly in sort of more altered and deformed intrusions where the layering is very deformed. This is a summary diagram of PG reefs and layered intrusions here. Most of them are sitting here. You see there the ultramafic rocks, the interlayered mafic-ultramafic rocks, and the solid mafic rocks. So most of the reefs are sitting here in most of the good reefs in global layered intrusions. There are some of the chromatites here in the Bushveld complex that contain some PG, but much less so. And then also in some cases we have contact style mineralization, and that will be the last part of the lecture today. That can be economic in some cases, right at the margins of these intrusions. But normally no mineralization or insignificant mineralization in the upper portions. Okay. This is how they mine these things underground in the Bushveld complex. So the reef, the Merensky reef, the mineralization often is in about 20, 30 centimeters. Now this is not how you can send a person. You need 80 centimeters, they figured out in South Africa. So the stope width is normally 80 centimeters, only the mineralization sits in the lower 20, 30 centimeters or so, sometimes only 10 centimeters. But as you can see, this is obviously challenging. This is a big safety problem. In the mines in South Africa, they still have every year about 10, 20 fatal accidents in the platinum mines. So this type of mining is on its way out. I think already at the moment, most of the underground mines in the Bushveld, or at least half of them, make no money. It's the big open pit mines now. That's the future of platinum mining. That's where they make profits now. This is getting too expensive and also too dangerous, really. This is a profile of the PG reefs that we did years ago. Here are the two chromatites, the pegmatoid in the middle. You see it's just for 10, 20 centimeters in this case, where the PGE This is the PGE here in red, platinum palladium in green and red. You see they're sitting with the two chromatite stringers, a little bit above, another 10 centimeters above, and then at 10 centimeters or 20 centimeters below, they have infiltrated into the floor rocks a little bit, the sulfides. That's the reef, just about 25, 30 centimeters in this case. So the stope width is about 80 centimeters. A lot of waste has to be mined too. The challenge in this case, it's not, in this case in particular, is that some of the good grades are sitting in the floor, and so the mine, when they design the stope, has to do constant testing essentially on a daily basis to see whether the mineralization has percolated a little bit into the floor. This is an important point. In the Bushveld, this is relatively insignificant, this sort of downward percolation and into the floor rocks. This is one of the reasons why the Bushveld is the key, the most profitable PGE deposit on Earth, because underground you can nicely see the position of the reefs where you make the money. The two chromatites, right? Easy to see underground. When you go to other deposits like the Great Dyke in Zimbabwe, the PGE mineralization has percolated much more pervasively into the floor rocks that are of similar pyroxenitic composition as the main reef, and you can't see it easily underground. So constantly, every day, they have to do extensive grade testing, sending the stuff to the lab, waiting for the results before they can continue developing the stopes and the development. So that is another reason, much less known for the economics of the Bushveld complex, that the reef is so clearly visible underground, easy to mine therefore. What's the main challenges here in understanding ore formation? The amount of sulfides in the reef is supercontactic. What was the mechanism of concentration? We looked at some of these. Raining down of sulfides here onto the top of the crystal pile, unlikely, because again the reefs are so narrowly confined and relatively sharp. The contacts between the reefs and the host rocks, supersaturation of magma due to magma mixing, intrusion of PG-rich magma, downward percolation of sulfide in mushes, upward infiltration in fluids and melts, and then finally sorting of cumulate mushes during sloping. I'm not going to go, I don't have time to go through all these things with you. If you're interested, I have a discussion. These things are discussed in a number of papers. For example, my own one in 2013 in Mineral Depositor gives a lot of sort of a detailed examination of all these different models. I'm going to show you towards the end a little bit more detail this model that I and Melanie and our collaborators have sort of developed in the last couple of years. So there is the first possibility, sort of a rain of sulfides problem. Cannot really explain the sharp context of the reefs, of many of the reefs, notably in the chromatite seams. Knife-sharp context, very difficult to explain. Supersaturation of magma and sulfide due to magma mixing. The original idea was maybe you mix something primitive with something evolved, and the mixture sits slightly in the field of sulfur supersaturation. We now know this does not work here, because you really need the magmas, the Bushveld magmas are strongly sulfur undersaturated. If you have some magma in the chamber here, being close to sulfur saturation, you bring in something primitive, being strongly undersulfur saturated, the mixture would be still strongly sulfur undersaturated. So it's unlikely that this sort of magma mixing triggers sulfur saturation. In the old days, we thought that the magmas are much more sulfur rich, and therefore a mixture between this and this may be locally sulfur supersaturated. We don't believe so anymore. I think hardly anybody. The other problem is when you look at the profile through the mineralized sequence here, there's Merensky, UG2, UG1, you see there the PGE peaks. UG1 chromatite, UG2 chromatite, there's the Merensky. The underlying, the floor rocks usually are quite PGE poor. There's the bastard reef, called bastard reef because it looks like the Merensky but is uneconomic, has much lower PGE contents, not mineable. So the floor rocks are PGE poor, the reefs are PGE rich. If these reefs would be the result of magma replenishment, the PGE mineralization would be the result of magma replenishment. As I just documented, the mixture of replenishing and resident magma should be sulfur undersaturated. So you would expect then the PG mineralization to occur in the upper portion of the cyclic units, not right at the base, okay? Unless there was percolation to the base. So for these reasons, these sort of magma mixing models are not that popular anymore. Also, of course, we have the reefs extending here over 400 kilometers strike length. How do you explain that in a sort of a pancake-shaped body if we form sulfur saturation in response to mixing of magmas in a pancake-shaped body? You need broadly similar mixing ratios everywhere at the two ends of this pancake, here and here. And this also seems difficult to conceive, really. Some people proposed that perhaps we had intrusion of very PG-rich magmas. Tony Neldon proposed that some time ago here. So he argues that the PG in the sulfides requires a very thick magma column. How can we accumulate sulfides so effectively here from more than 500 meters of magma? And he proposed then some kind of a plating out of sulfides. But the problem is, when we look at the reefs, actually we have these Rayleigh-type fractionation signatures of PGE. You see it goes down very rapidly here, exponentially. Very strong PGE enrichment at the base, and within a meter here, it dramatically decreases. So this is inconceivable if you have a 500-meter magma column to separate the PGE effectively into just a few decimeters. And the same problem for the chromatites, of course. How do you form these narrow layers with knife-sharp contacts from a 500-meter magma column? And then it just stops. So this is the same problem here for these PGE reefs, essentially. And the other problem is, when we look at all these colored dots here, these are the fine-grained sills in the floor of the Bushveld complex that we think are the parent magmas to the intrusion. And you see that all of them have PGE contents that are pretty much in the range of global basaltic magmas. Yeah? They all plot quite closely together. And there is not a single one that is dramatically enriched, as Naldud has requested there for his model, that we need some more PG-rich magmas to produce these narrow reefs. So I don't think that is really suitable. People have suggested as of recent that perhaps the Merensky reef is a sill-like body, that these reefs are sill-like bodies that were injected already containing sulfides from some staging chamber. And in fact, some of the field evidence suggests, yes, perhaps there could be sills. You see that this intrusion here seems to have injected into its roof. So this is a possibility, that perhaps the sulfide saturation was already reached at depth, but this is really just pushing the problem into a lower staging chamber. Perhaps some percolation of sulfide from a proto-rock that contained just very small amounts of sulfides and then slowly percolating down through the crystal pile, accumulating on top of these thin chromatite stringers. It's a possibility. We see textures where sulfides form these stringers, these subvertical stringers, suggesting perhaps that sulfides were mobile. And as I showed you earlier also, that we have sometimes sulfides below the Merensky reef, so there may be some percolation. And then there are some people who propose that the PG were introduced upwards through the semi-consolidated crystal pile here by late magmatic fluids and then precipitated here in the reefs, which may have represented at that stage the top of the crystal pile. So Woodrow from America is very prominent supporter of this model, but most people in the Bushveld do not follow this model. I think we have examples, for example, where the Merensky reef just sits about 100 meters above the top of the floor. In other words, if this is your Bushveld here, normally the Merensky reef. So there's a big locolytic body here. The Merensky reef does this sort of thing. It sits normally several kilometers above the floor, but in places where you go to the margins actually of the Bushveld, the Merensky reef does this sort of thing and can sit just 100 meters above the basement. It's still unchanged grade. So it seems quite clear that the grade of the Merensky reef is not dependent on the thickness and nature of the underlying floor rocks. So I think these ideas about the PG being transported from depth and are not generally considered viable anymore. And then, of course, my own model, the ones that Melanie and I have worked on in the past, is that the reefs really are the result of sorting of crystal mushes, sorting by means of gravitational and processes. In other words, denser crystals are separated from lighter crystals when crystal mushes are slumping towards the center of this progressively subsiding lockolytic bodies and being sorted due to gravitation, but also kinetic sieving processes. In other words, the smaller crystals, the smaller chromite and sulfide phases are sinking through the plagioclase and larger pyroxenes to concentrate and form these sort of layers of chromite and sulfide. So this sort of model we developed really largely because of all the evidence for deformation in many of the layered, particularly layered intervals that host the reefs. These otolith-rich rocks, you know, and little deformational features, little slumping structures and folds and so on, and potholes. And before I go to the models, I briefly have to show you, and I'm running out of time, I want to show you actually briefly a few slides of this, where the future of PG mining lies, in the contact-style mineralization, not in the deep internal reef-style mineralization, but in the contact reefs. And in terms of geological situation, we're sitting here now. So we looked at the internal reef so far in the center of the intrusion, but the Platt reef, the so-called Platt reef, the marginal style, contact style mineralization would be in a setting like this, where the critical zone is abutting on top of the basement rocks, and our reefs now, in my interpretation, the internal reefs are simply becoming more wider, more dispersed, faster cooling rates, not so efficient concentration of dense phases like sulfide and chromite. So much wider and lower grade reefs, but because they're wide, they are open pitable and therefore more economic. So this is what I'm going to show you now a number of pictures here, about 20 pictures quite quickly of the Platt reef. So we're essentially still at that Marinsky horizon here, but now at the margin of the intrusion. Okay? And whether that intrusion, of course, that margin of the intrusion is present depends on exposure. Okay, our exposure level of the Bushveld is something like this, that it does this here. Okay, so in other words, where the reefs are abutting against the margin is not everywhere exposed. Okay, so that is very important. So the place where it is exposed here is the northern lobe of the Bushveld complex. No? Here, in red is this sort of what we call the Platt reef, the critical zone where it's abutting against the margin, and you see it's cutting down actually through the entire Transvaal supergroup. There is the shales, dolomites, and then the Archean granite basement below it. So the critical zone is cutting down through that entire portion here, and there is a big, here at Sunslot is that big open cast Mokalaquena mine of Anglo-American. The rocks here are still noritic, gabbronoritic, and pyroxenitic, just like the upper critical zone Marinsky reef. We have them interlayered, but more chaotically now, not so regular. You see, we have here the more ultramafic and mafic rocks. We have them in coarser and finer grain sizes. We have otolith, lots of otolith, like we had in some of the internal rocks too. We had lots of little fragments and schlieren here of chromatite. In the gabbronoritic matrix, we have otolith, both of ultramafic and off-mafic locality, and locally we actually have quite significant sulfide, because here now the intrusion of course can interact with the floor rocks much more efficiently than in the internal reefs. So we locally have much higher sulfide contents, but these do not tend to be particularly PG rich, these sulfides. So there's a cross-section from the early work here. There is the granitic basement. There we have our pyroxenitic rocks, strongly contaminated with lots of xenolith here. There are big xenolith on the scale of meters to tens of meters of dolomite and calcsilicate in a sort of a gabbronoritic and pyroxenitic matrix. So this would be the layered, you see the layered pyroxenite and norite, gabbronorite rocks of the upper critical zone. But now they got huge xenolith here of the Transvaal supergroup. And associated with that now are disseminated sulfides. Large amounts of disseminated sulfides throughout before we come into the main zone up here. So the mineralized horizon is here up to 200-300 meters thick. The mineralization is not as concentrated as in the internal reefs, much wider and lower grade, but locally open pitable. That's what I'm going to show you. There is some dolomitic floor rocks, and with some sulfide mineralization injecting for a few meters to tens of meters, that the sort of brownish spots are sulfides in the dolomitic floor rocks. There's typical pyroxenite or melanorite of the Platte Reef with little bits of sulfide here. There's some mica, some flocopite mica, and there you see that fine-grained stuff on top. That is a calc-silicate xenolith. Yeah, and originally a dolomitic rock that's been turned into a calc-silicate. So little bits of sulfide everywhere. Coarse-grained to medium-grained with some flocopite, possibly resulting from floor assimilation, volatiles from the floor. So that's typical Platte Reef. And lots of other pictures here. There's another drill core intersection now. So we call these rocks very textured. They're variable textures and mineralogies. So more ultramafic to more mafic, finer grain to coarser grain, dolomite xenolith here. Lots of mica, flocopite mica in places, disseminated sulfides everywhere. That's what they mine. Here a big xenolith of calc-silicate, this sort of greenish stuff is now, it's essentially, you know, a diopside rock, rich in diopside, but also some calcic olivine and tremolite and rock and minerals like this, surrounded here by some alteration. Hello in a noritic, melanoritic Platte Reef rock, upper critical zone rock. And these contain then disseminated sulfides that are locally mineable. Here, some xenolith of shale in these rocks. This is a banded shale, locally quite sulfide rich. There's these locally sulfidic patches that result from assimilation of the shale. Not very PG rich. Again, very textured rocks here with some local cross-cutting veins of sulfide. We have locally rocks where very little sulfides are visible and still they are highly PG mineralized, so probably some late mobilization and resorption of sulfur by fluids, leaving immobile platinum group elements behind. We get here chromatite stringers in these rocks, so this is typical of critical zone, upper critical zone, but also associated here with some calc-silicates and hornfelds in a very textured gabbronoritic and pyroxenitic rock. We get some locally some pegmatoidal rocks with sulfide. Again, otolith, feldspathic otolith, chromatite stringers here, you know, and features that resemble critical zone elsewhere with these boulders, some massive chromatite layers, but everything much more chaotic, less ordered, less regular along strike. So that's the sort of Platte Reef. It's critical zone, but less orderly. I'll skip this. You see there is locally here chromatites, the UG2 chromatite, also with 2, 3, 4 grams per ton PG, so much less orderly, much regular. And we find in the Platte Reef mineralization over perhaps, in this case, about 100 meters. And there are noritic pyroxenitic rocks here separated by thick tens of meters of hornfeld xenolith or otolith, okay? So the Platte Reef in this case seems to be some kind of a sill complex, and again perhaps it's intrusion already of sills into a pelitic country rock sequence. And as you can see now, the grade is quite low here. It's about 1 gram per ton, as opposed to the Marinsky Reef 5, 6, 7, 8 grams per ton. Here's just 1 gram per ton, but it's what, over 100 meters. Okay, so if you add that together, that 100 meters over 1 gram per ton is 10 meters of 10 grams per ton. So there's a lot of PG in there, but just less concentrated than in the Marinsky Reef. So, you know, in some cases we have 20, 30 meters of 3 or 4 grams per ton. So that's really, really much more economic than the Marinsky Reef. It's simply a matter of concentrating these sulfides efficiently. This is some of the well mineralized rocks here in the Platte Reef. You see there's chalcopyrite. There is some pyrrhotite in the sort of bronzy colors, and the silvery mineral is pentlandite. That's the nickel-rich phase. It's typical magmatic sulfides in the Platte Reef. So a little bit more sulfide perhaps than in the Marinsky Reef, somewhat more concentrated. This is a profile we did years ago. Platte Reef at the margin here, low grade, just about 1 gram per ton, but over several tens of meters. And then when you go towards the interior of the intrusion, you see that we concentrated, and ultimately here we just have a narrow layer of Marinsky Reef and UG2 chromatite from the original tens of meters of low-grade mineralization. So we can trace that into the interior of the intrusion, that the marginal contact-style mineralization becomes narrower and more concentrated. And then also the bulk PG actually decrease when we go to the center. This is an interesting thing. Here, Ivanplatz is now drilling in the northern lobe, here from Plattreef near the surface down into the center of the intrusion. We see again the same thing. We find normal Merensky and UG2 in the center of the intrusion, and when we go to shallower levels, it becomes more and more chaotic and contaminated. And these are all floor rocks here in purple, dolomitic and palitic floor rocks, and it becomes more and more contaminated when we go to the margins of the intrusion. So I think this is this sort of is a good summary diagram of what's really happening here. When you go to the center, you see there you have normal lower zone, critical zone with UG2 and Merensky reef. Then you go to the margin, the lower zone is pinching out. We have critical zone directly overlying now the quartzite and palitic rocks, and the reefs now, the Merensky and UG2 reefs, become very wide and disturbed and irregular zones of very, very textured rocks. I think that's the message for exploration. That's what you have to look for. I'll skip this and this. There is a good example of one of the intersections that Ivanhoe is now drilling in the Plattreef here. Look at this. We have PG over about 40 meters running here in a spectacular intersection of something like 5 grams on average here, or 6 grams on average, 40 meters, 6.88. This is amazing. And they are sinking a deep shaft at the moment to mine this underground. So this is really spectacular. And we don't completely understand. You see over 90 meters, they have 4 grams per ton. So this is really much higher bulk PG contents than in the internal reefs. And we don't completely understand why this is so. So there is a sort of a schematic picture of perhaps how the sulfide reefs look like when you go to the interior of the intrusion. We may have a zone of contact at the relatively fast cooling contact zone where PGE are widely disseminated. Maybe that's the Plattreef. And then when we go towards the interior, slower cooling, the sulfides can slump towards the center. And we are left with a relatively regular narrow reefs that have much lower PG but more concentrated. And then towards the center, who knows what's in the center, but perhaps there is thick zones of very high-grade mineralization. We don't know. We will probably never know. It's easy to propose that for me. But yeah, so that's essentially the Plattreef. I'm going to skip this too. And this is where this is what Ivanhoe is now drilling here. There is the Plattreef in the northern lobe, and when we go down, it's sort of flattening out a little bit locally. This is where they find these very high-grade intersections here running at several tens of meters grade, which is why they call it the flat reef. And this is where we begin to have normal Merensky and UG2 chromatite when we go down into the interior of the intrusion here. I'm going to skip that one. Okay. Now, very little, I'm going to skip completely the PG in the main zone because they are essentially uneconomic. And so I'm going to skip that completely for time reasons. Just a few slides. Questions and paused. And briefly, a few slides on the magnetite layers. There are these, how much time have I got left? 15 minutes, okay. There are these 20 layers of massive magnetite here in the upper zone, of course, that are very important economically for vanadium, for the vanadium content. So we have a number, they contain a number of important ore minerals here, magnetite notably, but also ilmenite, olivespinel. So this is what is looked at by the mining companies, of course, for vanadium. This is how these things look like. Origins, the numerous origins have been proposed for massive magnetite layers. Again, gravitational concentration of dense magnetite, perhaps, or perhaps immiscibility of immiscible iron-rich liquids. It's explained here, and I'm not going to go into details now, but I personally don't believe in immiscible iron-rich liquids because the experimental evidence is not really consistent with it. But there is the main magnetite layer. You see it's a 1.5 meter thick layer that hosts significant vanadium mineralization. And there's a diagram a couple of years ago from Klim where he looked at the vanadium contents of magnetite layers in the Bushveld complex. And there's the base of the lower zone here. There's the lowermost magnetite layers and the uppermost ones here. And when you look at the vanadium contents, you can see that the vanadium content progressively decreases with height through the magnetite layers. And that is because vanadium is compatible into titanomagnetite. And so this is again very important for exploration. When you're looking for vanadium deposits in layered intrusion, you must find the lowermost magnetite layers. Okay, these uppermost magnetite layers here, there is one that is 20 meters thick. Okay, pure magnetite, titanomagnetite, but it's got no more vanadium left. So this is very important in exploration, that when you look at for vanadium, you need to go for the lowermost magnetite layers. And I look here, I compare actually chromatites and magnetites in terms of their exploration potential, and I don't have time to go through it in detail. You got it here, the two slides where I compare the two in terms of exploration significance. I'm also going to skip the hydrothermal and late magmatic PG mineralization because it's not important economically, globally. There are some pipe-like PGE deposits in the Bushveld complex that people believe formed in by contribution of hydrothermal fluids. I know that there's one or two of you who is interested in this, but I'm going to skip on this. Yeah, these sort of, ultramafic phases that appear to intrude downwards actually into the gabbronoritic sequence from further up. So very iron-rich magmas, but I don't have time to look at this. And there I have a few slides also for you. There's a lot of text. You can read it yourself to read a little bit on the hydrothermal mineralization at the top of the Bushveld complex. Overlying the Bushveld complex and intruding the Bushveld complex is a thick granitic phase, the so-called Lebova granites. And they have very significant tin, fluorite, and locally gold mineralization associated with them. And that's essentially hydrothermal. So you see all this pinkish stuff here in the center of the Bushveld. That's the late granite, slightly later granite, and it contains quite significant gold, tin and fluorite mineralization, and locally a bit of gold too. So again, I'm going to leave you with it. You can read it here. There are some references also, just 3 or 4 slides. And I'm coming to the summary now of the whole Bushveld complex, because I only got 10 minutes and I have to do this with you now. So in summary, when we look at this gigantic event here, PG mineralized intrusions obviously have formed through large degree mantle melting. They are rich in magnesium and nickel and chromium. They have high magnesium numbers. They are associated with Archean cratons in most cases. So the red dots here and yellow dots, these are the PG-bearing large layered intrusions. You see in Canada, the Fennoscandian craton in Europe, here in southern Africa, Yilgarn Pilbara craton, and then in Siberia. So we now have examples also in Amazonia. So they are associated with cratons. Why this is so, not entirely sure. It could be a larger degree of partial mantle melting in the Archean, could be a preservational feature. You know, these portions of the crust are up to 3.5 billion years old, so many more magmatic events are preserved there than in younger oceanic crust. It could also mean that, you know, we need the subcontinental lithospheric mantle in the origin of these features. I don't believe in this anymore, but certainly there's a spatial correlation that suggests perhaps this is required. In terms of age relationship, and this comes from a paper in Miram Deposa in 2011, you know that these mineralized layered intrusions, they all tend to be concentrated here, you see, at the beginning of supercontinent formation, all right? Mostly Archean, early Proterozoic, and usually during supercontinent amalgamation. Why is this so? We don't know. It's the same for other mafic-ultramafic events that host nickel deposits. And it could be that, you know, there's plenty of subduction here when supercontinents assemble, and subduction results in perhaps rollback and back arc spreading, allowing a magma ascent, or the subduction-related metasomatism of the subcontinental lithospheric mantle causes delamination and allowing astenospheric mantle plumes to ascend into the upper portions of the lithosphere. Or it could be related to plate collisions causing rupturing of the cratons and therefore for forming these sort of opening these deep lineaments that allow to drain magma reservoirs at the base of the lithosphere. It is possible that that at the base of the lithosphere here, if this is a craton, that we have portions here, that a very irregular base where we have portions of magma reservoirs from previous plume events that are suddenly drained when we have collisions of different cratons opening a lineament. Okay, so it's possible that that is... Basically, we don't know why layered intrusions are concentrated here during plate amalgamation and supercontinent amalgamation. That remains... This is another area that remains to be studied. In some of the intrusions, we have evidence for structural control simply because of the shape of the intrusions. Here, the Great Dyke is obviously a 500 kilometer long feature, just 10 kilometers wide, that must have some kind of a structural control. In the case of the Bushveld, there are these major crustal lineaments, here the Tabazimbi merchant lineament, that appear to control the emplacement of the intrusion. So there is evidence for structural control in some cases, but not in all. We know that the intrusions, most of them have a very strong crustal component here. The incompatible trace elements are enriched. Negative niobium, tantalum, titanium, these are crustal signatures. The isotopes are strongly enriched. In many of the large layered intrusions, PG contents, in many cases very high, fertile. This is difficult, of course, to reconcile with major crust assimilation. Remember, if these magmas here, they have PG contents at the upper end of the crustal of the terrestrial magma compositions. If these are the results of 30% or 40% of assimilation of crust, then the magmas prior to crustal assimilation must have had, 30-40% more PG. They would plot then far above any other terrestrial magma, so makes it even more difficult to understand. So that's a bit difficult to understand in terms of crustal contamination. Basically, we don't know whether these magmas come from the astenosphere or the lithosphere. I think I personally now feel that these are astenospheric magmas that are strongly contaminated. But there are still some people who strongly believe that these and many other continental flood basalts are derived from metasomatized lithospheric mantle. I feel that perhaps, what Bushveld magmas tap is portions of the astenosphere that are strongly enriched in PG because there may be some undissolved portions of late veneer floating around in the astenosphere. This remains to be tested too. I think I'm going to skip this. Cyclic units, yes, we have in the critical zone of the Bushveld complex, we have these cyclic units where PGE are concentrated at the base of ultramafic units, here in the Marensky Reef, the UG2, the UG1. Why this is so, we are not entirely sure. People have invoked a number of different mechanisms, magma mixing, magma replenishment. Melanie and I, we sort of favor a model whereby cyclic units actually, rather than representing the original replenishment of magma, are the result of sorting of crystal slurries that rush down towards the center of these big lopolitic and subsiding lopolitic structures. So it's a process of gravitation and kinetic sorting and sieving of crystal mushes that leads to the formation of pure chromatites and association of dense sulfides with dense chromite. I'm going to leave the main zone business here. So this is essentially, in a nutshell, the model here. We have big layered intrusion, lopolitic intrusion that subsides in the center due to crustal loading when it's building, when it's forming, when it's accumulating. The dense crust is subsiding in the center. We begin to slide these slurries towards the center of the intrusion and form the more massive layers, as shown here in a nutshell. Okay. An initial protocumulate that is poorly layered. When we begin to subside the center of the intrusion, the newly forming magma replenishing events that produce more of these poorly sorted cumulates here begin now to be sorted and sieved and form layers of pyroxenite, anorthosite, and chromatite. So the other question, of course, is could some of these things be sills, some of these layers? And yes, I strongly believe that there may be sills. So when we have these slurries here sliding down and running down on top of other slurries and on top of the cumulate pile towards the center of the intrusion, they may locally inject and forming sills of chromatite and perhaps pyroxenite. And so some of these things may represent sills. We've looked at these potholes here, including the anorthosite potholes. I feel that these anorthosite potholes are the result of flexing and stretching of the cumulate pile. So in other words, when you have there is your cumulate pile, and the top of the cumulate pile here with various layers here is maybe not completely solidified. We have a lot of pull now down of these dense, particularly dense intervals towards the center of the intrusion, and so locally we may open up here sort of pull apart structures where this thing is moving down, and so overlying crystal mushes may then slump down into these forming potholes. And this may, in my opinion, may form potholes. Large potholes are the result of pull apart structures, so flexing of cumulate piles during subsidence. And here are a couple of pictures of these things. We can see these evidence for this flexing and deformation in these anorthosite potholes by means of these elongated schlieren. And I'm going to skip this one. So if this is all correct, then of course the key question is what happens in the centers of these intrusions. We don't know in the Bushveld. We probably will never know because the center is at depth, at great depth, even so much so that we can't pick it up geophysically. But in some other layered intrusions, we do have some evidence. We do know what's happening in the center. One is Kemi here in Finland, at the border to Sweden, where we have a layered intrusion that's standing sideways, on its side essentially. So in other words, this is the surface, and there is a layered intrusion. This is the base here. So there is the ultramafic rocks. And there is the mafic rocks. An intrusion that has been deformed, so it's almost standing on its side, and with a thick ore layer in the center, and then thinning towards its margin to just a few centimeters. A thick chromatite horizon that is up to 100 meters thick in the center, and then thinning to a few centimeters at the margins. So here you can see in the cross section the chromatite up to 100 meters thick here, and when you move towards the margin of the intrusion, just a few centimeters, there is the cross section. This is a diagram from a Geological Survey of Finland and Huchtelin a couple of years ago. So very thick, unusually thick chromatite here in the center of a layered intrusion. The key question, of course, is would we find something similar in the Bushveld complex if we ever had exposure? That is difficult for us to say, and this is, I think, my final slide. So layered intrusions, very complex systems, multiply replenished, lots of magma mixing and mingling, but importantly also slumping and reworking of cumulates when these bodies subside in the center. Ore formation controlled by fractionation and phase sorting. High-grade ores occur in flow dynamic traps and in the center of intrusions. That's the postulation. I think that is the last slide, right? Yep. Oh, there was a bit of a rush now towards the end. So what is now? Are there questions or what?
Yeah.
Okay. From here and also the other audiences or what? Can they also ask questions?
1 minute delays.
Okay, I see. It must have been a little bit overwhelming, no? But it was a bit in a rush at the end.
Did you see different population of chromite or magnetite?
Different what?
Population of chromite or magnetite in the different zone and in between cumulate and intercumulate?
Well, you know, as I said, the chromatite seams and the magnetite seams are often knife sharp, but between the knife sharp seams are also zones of disseminated chromite and magnetite. In other words, we interpret those as much less efficient sorting and sieving. You know, I mean, the effectiveness, the efficiency of the sorting and sieving process would be controlled by both the magma replenishment, the degree of subsidence, and also the degree of subsidence after and the time interval between magma replenishment and subsidence. So, you know, unless you had magma replenishment followed by subsidence, the sorting will be inefficient. The newly forming, the crystal mushes will have cooled too far already to be efficiently sieved. So there's sort of a number of features that have to come together to allow the formation of massive seams. And
what is the genetical relationship between ultramafic complex in Bushveld and associated granitic rocks that you mentioned that are slightly younger?
It's also something that much more research needs to be done on. There were a couple of studies, and it appears that the isotopic signature of the Nebo granite, that Lebova granite suite, is identical to the ultramafic rocks. This suggests to people who worked on this on these rocks that the granitic rocks may be differentiates of the ultramafic rocks. This is a little bit of a difficult to understand, to believe, because the Lebova granite suite is one of the largest granite massifs on Earth. So if that is correct, that would mean that one of the largest granite accumulations on Earth would be the result of fractionation rather than partial melting of the crust. So that is a bit tricky to understand. So, that's all we know so far. Remarkably little research has been done on the origin of the Lebova granite. There were maybe 5 papers. That's it. And the reason is that in terms of compared to the ultramafic rocks, the mineralization of the granite is relatively insignificant. And all mined out. The tin mineralization is largely mined out already since the 1970s. So. Other questions?
No, nobody asked.
Okay.
But I know it's a lecture instruction, so maybe.
Yeah, we have to stop.
Yeah.
Good.
I'm really sorry. But if you have any question, I guess you can send some emails to Wolfgang.
Yes, absolutely.
We will be around for the lunch, so if you have questions also, you can come. So maybe you need to process a little bit. Okay, so thank you everybody to came.
Should I bring